offering a solid foundation for anyone preparing for the professional engineering exam or simply looking to understand how our power grid are managed daily, you know. So, as I briefly discussed about myself in the previous session, so we will now skip this slide. I have created a YouTube channel for my courses where I upload my lecture and educational materials. Most of the content is related to my course today are coming from this link, Power Transmission and Distribution course. And you can find additional explanation and learning resources that there as well. So please subscribe to my channel if you think this is useful and you can use them. Okay. All right. First, we will begin with a fundamental overview of power systems. This section is designed to establish a strong foundation by exploring the architecture of a utility AC power system from the generation of electricity all the way to its distribution to end users. We will then delve into several key concepts essential for understanding power system operations, including voltage regulation, how to maintain stable voltage levels across the grid, power quality, the characteristics of electricity that enable it to be used efficiently by equipment, distributed generation, the integration of smaller decentralized energy resources like solar panels and wind turbines, power flow, the momentum of electrical power from generating source to loads, and stability, the ability of the power system to remain in a state of equilibrium under various disturbances. So the second, next, we will shift our focus to the critical role of substations and their equipment. This part of the presentation will provide a detailed look at the physical components that make up the grid infrastructures, and topic will include type of substation, comparison of air insulated or AIS and gas insulated GIS substations, highlighting their design and applications. GIS components, a specific look at the role of SF6 gas in GIS, its properties, and why it is used for insulation and arc quenching. So substation operation and another topic, and explanation of how substations are operated, including the function of key equipment such as switch gears, circuit breakers, and bus bars, as well as the practices for safe maintenance. So HVDC transmission, finally, we will explore HVDC transmission, covering its arrangements, performance, characteristics, and operational advantages. Then, in the cables and transmission lines, we will discuss the critical components that form the backbone of the power grid. Line characteristics, we will cover the different type of cables and transmission lines, their fundamental parameters RCL, and the skin effects, which influences current distribution. So performance and maintenance. I will explain how to measure dielectric resistance and capacitance, the standard testing procedures and the techniques used for fault location along the lines. Mechanical and electrical analysis, we will also look at the mechanical aspects such as sag and tension, and key electrical concepts like maximum power flow and line loadability. Then in system analysis and operation, uh, this part of the presentation is dedicated to the analytical and operational tools used in power system engineering. So, including the power system modeling, we will explore how to model power system using bus admittance and impedance matrices, load flow analysis. I will explain the different methods for solving load flow problems, including the Gauss-Seidel, Newton-Raphson, and fast decoupled methods. Advanced topics, we will briefly touch upon more advanced subjects such as optimal power flow fault analysis and short circuit analysis. Stability, finally, we will cover the fundamental concepts of power system stability and methods used to enhance it. And then I will talk briefly about power quality and control. The final section will focus on the important topic of power quality and its control, including the power factor correction. We will discuss how to determine capacitor values for power factor correction and their impact on the system. Then voltage support. I will explain the functions of shunt reactors and static VAR compensator species in providing voltage support. Power quality issues, we will identify and discuss common power quality problems such as voltage sag, soil, and total harmonic distortion. Standard, I will introduce important international standards like IEEE 519 and IEC 661 000 that govern power quality. So harmonic reduction techniques. Lastly, we will explore practical techniques for reducing harmonies in the power systems. So then we have grounding practices. This section is crucial for ensuring the safety and reliability of any power system. We will cover the practical and theoretical aspects of grounding, which is essential for protecting both equipment and personnel. Practical design, I will discuss the various grounding arrangements designed for different parts of the system, including transmission lines, substation, and consumer facilities. We will look at the specific design and considerations for each. Grounding standards, we will examine the important national and international codes and standards that governs grounding practices to ensure compliance and best practice. Then a key topic will be the effect of high grounding resistance on safety and protection. I will explain how improper grounding can lead to dangerous conditions and equipment damage. So finally, we will go over the specific procedure for grounding resistance measurements to ensure that systems grounding is effective and meets all safety requirements. So um, this chapter introduces the fundamental structure and operational principles of utility AC power systems. It provides an overview of how electrical power is generated, transmitted, and distributed through interconnected networks to ensure reliable and efficient energy delivery to end users. So the session focusing on key components such as generation units, transmission lines, substations, and distribution systems, highlighting their roles within the overall power system architecture. In addition, it emphasizes system reliability, voltage levels, grid interconnections, and the importance of maintaining stability and power quality in modern utility networks. So the power system is a complex and interconnected network responsible for delivering electricity from where it is generated to where it is consumed. This process is often referred to as the journey of electricity. It begins at generation plants where various energy sources such as fossil fuel, nuclear power, hydropower, and or renewable like solar and wind are converted into electrical energy. From there, the power undergoes a critical transformation at a step-up substation. The voltage is significantly increased, sometimes to hundreds or of thousands of volts. This is a crucial step for efficient transmission, as higher voltage reduces current, which in turn minimize the Ri2 power losses that occur over long distances. After the voltage has been stepped up, the power enters the transmission stage. So this is the bulk power transfer highway, where high voltage transmission lines carry electricity over long distance across the country. These lines are supported by tall towers and are designed to transmit massive amounts of power with minimal losses. So upon reaching a target region, the power enters a series of step-down substations where the voltage is progressively reduced to more manageable levels. So the first reduction prepares the power for regional distribution, while subsequent reductions make it safe and usable for local networks and end users. So the final stage is the distribution network, which is the local grid that delivers power directly to residential, commercial, and industrial consumers. This network is made up of smaller substations, transformers, and distribution lines that spread out through communities. The key components of the entire system, generation plants, transformers, transmission lines, substations, and distribution networks, must work together seamlessly to ensure a reliable and efficient power supply. So the reliability of this system is paramount, as it underpins virtually every aspect of modern society, from our homes and business critical infrastructure like hospitals and transportation systems. Therefore, understanding the architecture and operation of this system is fundamental for any engineer in the field. So this slide delves into the fundamental concepts that govern the day-to-day operation and reliability of power system. These concepts are essential for understanding how engineers maintain a stable, efficient, and high quality power supply. So the first one is voltage regulation, which is the process of maintaining a stable voltage level within a power system regardless of changes in load. So a stable voltage is crucial for the proper operation of electrical equipment. If the voltage is too low, equipment may not function correctly or could be damaged. Conversely, if it is too high, it can lead to insulation breakdown and equipment failure. Voltage support is achieved using devices like transformers with tap changers, capacitor banks, and voltage regulators, which inject or observe reactive power to keep the voltage within acceptable limits. So this ensures that every appliance, from a simple light bulb to complex industrial motor, receives the correct voltage. Uh, Another content is power quality, refers to the consistency and reliability of the electrical supply. A high quality supply is one that is free from disturbances such as voltage sags, short-term dips in voltage, soils, short-term increases, and harmonic distortion in the pure sine waveform. Poor power quality can lead to equipment malfunctions, premature aging of devices, and even complex system failure. So the presence of harmonics, for example, can cause overheating in transformers and motors. Engineers use various techniques such as filters and active power conditioners to mitigate these issues and ensure that the power delivered is a clean and stable sine wave. So another content is distributed generation, or DG, involves the use of small scale power generation sources located near the point of consumption rather than the large centralized power plant. Examples include rooftop solar panels, wind turbines, and microturbines. And DG is a rapidly growing field that fundamentally changes the traditional power grid model, and it can improve grid efficiency by reducing transmission losses, enhance grid reliability by providing local power sources, and support the integration of renewable energy. However, it also introduces challenges related to grid management, stability, and control, as power can now follow in multiple directions. So this is another issue we call hosting capacity. So another subject is power flow, also known as load flow, is the movement of active power measured in watts and reactive power measured in var through the power system. It is a crucial analysis tool for system operators and planners. A power flow study calculates the voltage, current, and power at every bus node in the system under a given set of conditions. This analysis helps engineers understand how the grid is operating, identify potential bottlenecks or overload, and plan for future expansions. It is a fundamental calculation in both steady-state analysis and dynamic simulations. The last thing is power system stability, is the ability of the system to return to a state of equilibrium after being subjected to a disturbance, such as a sudden change in load or a short circuit fault. Stability is a measure of the system's robustness. A stable system can withstand these events without losing synchronism or experiencing widespread blackouts. So there are different types of stability, including rotoring angle stability, voltage stability, and frequency stability. And engineers use various methods such as power systems stabilizer and FACS devices to enhance stability and ensure the grid remains resilient and reliable. Okay, this slide focused on two primary architecture for electrical substations: air insulated substations, or AIS, and gas insulated substation, GIS. The choice between these two design is a critical decision in power system engineering, influenced by factors such as available space, environmental conditions, and cost. Air insulated substations uses ambient air as the primary insulating medium between its live electrical components. This is the traditional and most common type of substation, often seen as a large, often open air network of bus bars, circuit breakers, and isolators. And the open air design means that components are spaced for part of the prevent arcing through the air. So this required a significant amount of land, making AIS less suitable for urban areas where real real estate is expensive. AIS has a long history of reliable operation, and it's relatively easy to maintain due to the accessible nature of its components. However, its performance can be affected by environmental factors such as pollution, humidity, and weather conditions, which can lead to flashover or insulation degradation. Another substation type is GIS. GIS uses sulfur hexafluoride or SF6 gas as the insulating medium. The gas is colorless, odorless, and non-toxic compound with an extremely high dielectric strength for superior to that of air. So in a GIS, all key components such as bus bars, circuit breakers, and disconnectors are included in sealed gas-filled metal tanks. This compact includes design allows for much smaller footprint, often requiring only 10% of the space needed for comparable AIS. So this makes GIS an ideal solution for urban environments, underground installations, or areas with limited space. The sealed nature of GIS makes it highly reliable and largely unaffected by external environmental factors like pollution, moisture, and extreme weather. So this results in minimal maintenance and a longer operational lifespan. However, the initial cost is higher, and maintenance, when required, can be more complex due to the inclusive nature of the equipment. So this slide explores the crucial role of sulfur hexafluoride gas, a key component in gas insulated substations, GIS. Its unique properties are what enable the compact, high performance design of these modern electrical facilities. So, what is SIF gas? SF6 gas, sorry. SF6 is an inert, non-toxic, and non-flammable gas. It is a man-made compound composed of one sulfur atom and six fluorine atoms. So while it is a potent greenhouse gas, its use in substations is carefully managed in a closed loop system to prevent leakage. So its exceptional electrical properties make it the preferred medium for high voltage insulation and arc quenching. So we have key characteristics has been listed here in two items: high dielectric strengths. This is the most important characteristics of the SF6. Its dielectric strength is about 2.5 times higher than that of air and 10 times higher than that of insulating oil. So this superior insulating capability allows for a drastic reduction in the spacing between the live electrical components, leading to the highly compact design of GIS. This is the primary reason for why GIS takes up so much less space than the traditional AIS. So another key characteristic is excellent arc quenching properties. So when a circuit breaker operates to interrupt a high voltage current, and electrical arc forms, SF6 gas has an exceptional ability to absorb the energy from this arc and rapidly cool it down, extinguishing it almost instantly. This rapid arc quenching minimizes wear on the breaker contact, increases the operational lifespan of the equipment, and enhances system reliability. And regarding practical applications, due to its superior insulating and arc quenching capabilities, SF6 is a workhorse in GIS equipment. It is used as the insulating medium in circuit breakers, disconnectors, and bus bars. The gas-tight enclosures ensure that the equipment is protected from environmental contamination, which further contributes to its high reliability and minimal maintenance requirements. In summary, SF6 is not just an insulator, it is a fundamental enabler of modern, compact, and highly reliable high voltage electrical equipment. So this final slide serves to recap the key takeaways from the presentation and reinforce the central message. that the power system is a crucial and constantly evolving piece of our modern world. So, um, recap of the main points are listed in the are itemized here in this slide. First of all, the structure flow of power, reiterate the linear yet complex journey of electricity, and begin with generation where power is created, more move to transmission, the long distance highways of the grid, and conclude with distribution, the local delivery to homes and business. This structure flow is the foundation of the entire system. The next item is the importance of key operational concepts. Summarize the fundamental principles that show the system operates radially. Um, remind you significant of power quality, a clean and stable supply, power system stability, the ability to withstand disturbances, and the importance of maintaining proper voltage regulation and support. So another things is are advantages and differences between IIS and GIS. Briefly highlight the contrasting substation architectures. So AIS are the traditional space use and simpler design, while GIS are the modern, compact, and highly reliable alternative, either for space constrained environments. So final thought is that end of the presentation with a forward-looking perspective. The continuous evaluation of power system architecture is essential for several reasons. As global energy demands grow, the grid must become more efficient and robust. Simultaneously, the increasing integration of new technologies, particularly distributed generation like solar and wind power, requires the grid to adapt from the one-way to a multi-directional power flow system. So the key concepts cover are substation equipment and maintenance. We will learn about the different types of substation switchgear, single and double chamber, and the procedure necessary for safe maintenance. We will also understand the function and operation of essential substation equipment, including circuit breaker, bus bars, fuses, measuring instruments, and disconnections. HVDC transmission, a detailed objective is to recognize the arrangement, performance characteristics, and the operation of high HVDC systems. Then we will explore the principle behind the optimal sizing and placement of DG within a power system to maximize efficiency and reliability. Uh, After that, several objectives are dedicated to core power system analysis techniques. We will understand the concept of power system modeling using the bus admittance and bus impedance matrices. We will also cover different load flow analysis techniques like the Gauss-Seidel, Newton-Raphson's, and fast decoupled methods. So we will learn how to recognize the solution to the optimal power flow problems, which seeks to operate the system at the lowest cost. This course will also cover how to recognize different faults in power system and perform short circuit analysis. Finally, stability. The final object is to understand power system stability and the various methods used to enhance it, ensuring the grid remains resilient under disturbances. Okay, switch gears is a general term covering a wide range of switching devices, including circuit breakers, disconnectors, and fuses used to control, protect, and isolate electrical equipment in a substation. The specific arrangement of these components, often referred to as the switchgear architecture, is crucial for both operational flexibility and safety. This slide compared to common configurations, single chamber and double chamber switches. So single chamber switches is the straightforward and cost-effective design where a single circuit breaker is used to control and protect a single power lines or transformer. In this arrangement, all associated components such as the bus bar, circuit breaker, and isolators are housed within a single electrical section. So while this design is simple and has smaller footprint, it presents a significant operational limitations. So any maintenance or repair work on the circuit breaker requires the entire line to be de-energized and taken out of service. This results in service interruptions for all connected consumers, making it a less flexible option for critical infrastructure. For safety, the procedures are paramount. Before any work begins, the line must be completely disconnected from all power sources, verified to be a zero voltage and properly grounded to prevent accidental re-energization. So double chamber switches configurations, also known as a double busbar or bypass systems, offers a much higher degree of flexibility and reliability. The key difference is the presence of a second or bypass busbar. So this allows for a line to be temporarily switched to the second busbar while its primary circuit breaker is isolated and taken offline for maintenance or inspection. So, and the last thing is maintenance and safety protocols, regardless of the switchgear types. The safety of the personnel is the highest priority. A strict protocol must be followed to prevent electrical accident. This protocol includes lockout or tagout procedures, which ensure that all energy sources are isolated and physically looked to prevent accidental re-energization. Proper grounding is also essential. A circuit must be connected to the earth to ensure that no residual voltage remains. Finally, all maintenance work should only be performed by trained personnel using specialized insulated tools and personal protective equipment, such as gloves, face shields, and flame resistance clothing. So these measures ensure that even in the case of an unforeseen scene, even the risk to personnel is minimized. So substations are the heart of the power grid, and their safe and reliable operation depends on a variety of critical components. This slide provides an overview of the most essential equipment found in a typical substation, explaining their function and operational purpose. So, first of all, circuit breakers. Circuit breakers are high voltage mechanical switches designed for both protection and control. Their primary function is to automatically interrupt the flow of current in the event of a fault, for example, a short circuit or overcurrent. They can also be opened and closed manually for routine maintenance or system reconfiguration. So when a fault occurs, a circuit breaker must extinguish a high energy electrical arc that formed between its contacts as they open. To do this safely and quickly, it uses an arc quenching medium such as SF6 gas, insulating oil, or a vacuum. The rapid extinction of the arc prevents damage to the equipment and protects the rest of the power system from the fault. Another part is a bus bar. Bus bars are conductive bars, typically made of copper or aluminum, that serve as a common connection point for multiple incoming and outgoing electrical circuits within the substation. They are essentially the electrical highways that allow power to be efficiently routed from one part of the substation to another. The layout and design of the bus bar system are crucial for the substation's reliability. A well-designed bus bar arrangement provides flexibility, allowing a specific circuit to be isolated for maintenance without disrupting the entire substation. Fuses. A fuse is a simple but effective overcurrent protection device. It contains a wire or metal strip that is designed to melt and break the circuit when the current following through it exceeds predetermined safe level. Unlike a circuit breaker, a fuse is a one-shot device. Once it melts, it must be replaced. Fuses are often used for the protection of smaller loads or as a backup to circuit breakers, providing an additional layer of safety against excessive currents. Another thing is measuring instruments. To monitor and protect the power system, it is necessary to accurately measure high voltage and currents. CTs and VTs are known as potential transformers, or PTs are used for this purpose. So they are designed to safely step down the high voltage and current levels to much lower manageable values that can be read by monitoring instruments and protection relays. So these instruments provide crucial data for system operators, allowing them to monitor the health of the grid, detect anomalies, and trigger protective actions when necessary. Without CTs and VTs, it would be impossible to safely measure or control high voltage power systems. And the last one is disconnectors. A disconnector or isolator is a mechanical switch that used to physically isolate a section of a circuit or bus bar. It is not designed to interrupt current, so it can only be operated when there is no current following through the circuit. So these connectors are primarily used for safety. They provide a visible physical gap in the circuit, which is a key part of the layout or tagout procedure, ensuring that section of the grid is completely de-energized for maintenance and repair work. This slide explores the concepts of HVDC transmission, technology that complement traditional AC power systems. While most of the power grid operates on AC, HVDC offers significant advantages for specific applications, particularly for long distance and undersea power transfer. So an HVDC system fundamentally consists of a transmission line connecting two converter stations. At the sending end, a rectifier station converts AC power from the grid into DC power. This DC power is then transmitted over the HVDC line. At the receiving end, an inverter station converts the DC power back into AC power, which is then fed into the local AC grid. This two-step conversion process is what makes HVDC distinct from conventional AC transmission. So the most significant advantage of HVDC is its efficiency over long distance. In AC transmission, power is lost due to the reactive power flows and skin effect. HVDC, however, only transmits active power, which substantially reduces the line losses. For very long distance, the cost saving from reduced energy losses can offset the high cost of the converter station. So we can use HVDC, and HVDC can connect two power grids that are not synchronized or operate at different frequencies. This is particularly useful for international power transfers or for connecting grids with different operational characteristics. The converter stations act as a buffer, allowing the two systems to operate independently of each other. So the scaling effect is a phenomenon in AC transmission where current tends to follow near the surface of the conductor, increasing the effective resistance and power losses. Because DC current flows uniformly through the entire cross section of the conductor, HVDC lines do not suffer from this issue, leading to higher efficiency. So while the initial investment in HVDC converter stations is high, their operational benefits for long distance high power transfers are substantial. They are an ideal solution for uh, connecting remote generation sources and submarine cable applications, and stringing asynchronous grids, and we can use for this kind of applications. This slide focuses on the mathematical and analytical tools used by power system engineers to understand, plan, and operate the power grid. Modeling and analysis are fundamental to ensuring the system reliability, efficiency, and stability. So, first of all, power system modeling is the process of translating the physical components of the electric grid, such as generators, transmission lines, and loads, into a mechanical representation. This allows engineers to simulate the behavior of the system under various conditions, from normal operations to severe faults. The most common form of this representation is the network matrix, which is used in various analytical studies. Bus admittance, or Y bus, and bus impedance, Z bus matrices. These two matrices are fundamental tools for power system analysis. They represent the network's electrical characteristics and are used to solve for voltages and currents throughout the grid. The Y-bus matrix relate the current injected at each bus node to the voltages at those buses. It is a sparse matrix, meaning most of its elements are zero, which makes it computationally efficient for load flow analysis. The Z-bus matrix relate the bus voltage to the current injected at each bus. It is particularly useful for short circuit analysis, as it can quickly calculate the fault currents that would follow at various points in the systems. Load flow or power flow analysis is a critical study that calculate the steady state operating conditions of a power system under a given load. The goal is to determine the voltages, currents, and power flows at every bus in the network. So several iterative methods are used to solve the complex nonlinear equations, involve Gauss-Seidel method or Newton-Raphson method, and fast decoupled method. In Gauss-Seidel method is a straightforward iterative technique that is easy to program. However, it converges slowly and may struggle with larger, more complex systems. Newton-Raphson method is a more powerful and widely used method that converges much faster and more reliably than Gauss-Seidel. It requires more computational efforts per iteration, but is preferred for its speed and robustness on larger scale power systems. Fast decoupled method is a simplified and faster version of the Newton-Raphson method. It makes certain approximations to reduce the number of calculations, making it an excellent choice for online control and real-time analysis where speed is a priority. Optimal Power Flow is a sophisticated analytical tool that goes behind simple load flow analysis. It is an optimization problem that aims to find the best operation point for the power system while satisfying all physical and operational constraints. The objective is typically to minimize cost function. It means the total cost of generation while ensuring that voltage limits, power flow limits, and other operational criteria are met. Operational power flow is essential for making the power grid as efficient and economical as possible. This slide covers two critical aspects of power system operation: faults, which are inevitable occurrences, and stability, which is the system ability to recover from them. So a robust power system must be both protected from and resilient to these events to prevent widespread blackouts. So faults in power systems is an event that causes an abnormal flow of current deviating from the intended path. The most common and severe type of fault is short circuit, which occurs when a direct connection is made between two or more conductors or conductor U and ground. Faults are categorized as symmetrical and or asymmetrical. Symmetrical faults, such as three-phase short circuit, affects all three phases equally and are relatively rare. Asymmetrical fault, like a single line to ground fault or a line to line fault, are more common and create an imbalance in the system. Short circuit analysis is the study of the fault conditions to determine the magnitude of fault currents. The result of this analysis are crucial for designing and selecting appropriate protective devices such as circuit breakers and fuses that can safely interrupt the fault current without damaging the equipment. Another subject is power system stability, is the ability of power system to regain its equilibrium after a disturbance, such as a fault or a sudden change in load. A system is considered stable if all generators remain in synchronism with each other and the system frequency and voltage return to acceptable levels. Uh, Engineers use various methods to enhance stability and ensure the grid resilience. This includes power system stabilizer, fax devices, and fast acting protections. So, power system stabilizers, or PSS, are control devices that are installed on generators. They introduce a damping signal to the generator's excitation system, which helps to suppress oscillations and improve the system ability to maintain synchronism. Uh, Fax devices, as I told you before, are a family of electronic controllers that improve power transfer capability and enhance stability. Examples include SVC and Tyrosol Control Series Capacitor TCSC, which can quickly inject or observe reactive power to regulate voltage and dampen oscillations. Fast acting protections. So when regarding this method, The speed at which a fault is detected and clear is paramount. So the faster the protection system operates to isolate the fault, the less chance there is for the disturbance to spread and cause a widespread outage. This is a primary reason why modern protection relays are designed for high-speed operation. Okay, based on this slide, we will now focus on the technical aspects of cables and transmission lines, and covering the following learning objectives. Cable and line characteristics. We will start by understanding the different types and the characteristics of both underground cables and overhead transmission lines. This includes grasping the significance of the skin effect and the techniques used to minimize it. We will also define and recognize the meaning of the reflection coefficient, surface roughness, and fundamental R, C, and L parameters for these lines. Testing and maintenance. This section will be practical, focusing on the procedure for measuring the dielectric resistance and capacitance of cables. We will also covering the general testing and maintenance procedures for both cables and transmission lines, and the specific techniques used for identifying fault locations. Finally, we will dive into key analytical concepts. We will learn how to analyze sag and tension in overhead transmission lines, and we will understand the concept of maximum power flow and line load ability. This introductory slide provides a high-level overview of how electrical energy is transported from where it is generated to where it is consumed. The objective is to introduce two fundamental methods of power transmission, overhead transmission lines and underground cables, and to highlight their key differences. Um, uh, the power system is often referred to as a grid because it is an interconnected power. At the core of this network are the transmission systems that act as the vital links carrying electricity over vast distances. We will focus on two primary methods. Overhead transmission lines, the most common and visible form of power transmission, and underground cable, a less visible but equally important method, particularly in um, densely populated area. So the key differences between the overhead transmission line and underground cables are uh, can be summarized in several things we will discuss later in the following slides. This slide provides a detailed look into the two primary methods of power transmission: underground cable and overhead lines. The choice between these two is a critical engineering decision based on the careful balance of cost, reliability, environment, and visual impact. So underground cables are a vital component of modern power grids, especially in populated urban area and suburban areas where space is limited and visual aesthetics are important. So we have a different type, paper insulated lead cover or PILC, and all the technology that uses paper as insulation and a lead sheets for moisture protection, while reliable it is being phased out in favor of newer materials. XLPE, crosslink polyethylene, so the most widely used type of modern cable. It offers excellent electrical properties. It resistance to heat and moisture and is lighter and easier to install than PILC cables. Gas insulated, used for very high voltage applications. These cables use um, pressurized gas like SF6 as an insulator. They are very compact and highly reliable. If I wanna summarize the characteristics of these cables are can be summarized as high reliability, low visual impact, high cost, complex repair, and thermal limitations. Regarding the overhead transmission line, are the traditional and most common method for transmitting power over long distances, forming the arteries of the interconnected power grid. So we have different types: aluminum conductor, steel reinforced, or ICSR. This is the most prevalent type of conductor. It combines the low weight and high conductivity of aluminum with the mechanical strength of the steel core, allowing it to span long distances between towers. The main characteristics are cost effective, high power capacity, easier to maintain, vulnerability to weather, and significant visual footprint. So, uh, okay, this slide focus on the skin effect, a fundamental and important phenomena in AC electrical systems that affects the performance and efficiency of power transmission lines and cables. Understanding this effect is critical for the proper design and operation of the power grid. So the skin effect is the tendency of AC to follow primarily near to the outer surface or skin of the conductor. In a DC system, current is distributed uniformly across the entire cross section of the conductor. However, in an AC system, the rapidly changing magnetic field created by the current induces eddy currents that push the main current toward the outer edges. So this non-uniform distribution effectively reduces the usable cross-sectional area of the conductor. And uh, regarding the consequences, this reduced effect area has two significant consequences. First, elastic resistance. Since the current is confined to a smaller area, the resistance of the conductor appears to be higher than its DC resistance. This phenomena is known as AC resistance. Higher power losses. The increased resistance leads to greater power losses in the form of heat, Ri2 losses. This reduces the overall efficiency of the transmission line, a major concern for long distance power transfer. And regarding the mitigation, to um, counteract the skin effect and improper efficiency, engineers employ several strategies in conductor design. First of all, aluminum conductor steel reinforced, and this is a very common solution. It uses a strong steel core for mechanical supports surrounded by a large volume of aluminum conductors. Bonded conductors. This method involves grounding multiple smaller conductors to act as a single phase. By doing this, the total effective surface area is increased, which significantly reduces the skin effect. Bonded conductors are particularly effective for high voltage transmission lines. Hollow conductors, in some cases, conductors are designed with a hollow core. This removes the least used part of the conductor, the center, while maintaining a large other surface area for current flow. So understanding the skin effect is very vital for designing efficient transmission systems and selecting the right conductors for given applications. Okay, this slide delves into the fundamental electrical parameters that define the behavior and performance of a power transmission line. These parameters from the mechanical basis for analyzing power flow, voltage regulation, and system stability. They are essential for engineers to design a safe, reliable, and efficient power grid. First of all, bus admittance and impedance. These are two matrices, Y bus or admittances and Z bus impedances that are central to power system analysis. And the Y-bus matrix represents the network admittance, which is a measure of how easily current flows between buses or nodes. It is particularly useful for load flow analysis, a study that calculates that steady state voltage and the power flow conditions of the grid. The Z-bus matrix represent the network impedance, which is a measure of the opposition to current flow. It is the inverse of the Y-bus matrix and is primarily used for short circuit analysis, which helps engineers calculate the magnitude of fault currents. Um, the reflection coefficient um, is a reflection coefficient symbolized by gamma is a parameter used in transient analysis to describe how voltage and current waves behave when they encounter a discontinuity, such as a load at the end of the transmission lines. And it is a ratio of the reflected wave to the incident wave. A value of 0 means there is no reflection, a perfectly matched load, while a value of 1 indicates a complete reflection, an open or short circuit line. So this concept is crucial for understanding surge analysis, which involves studying high voltage transients. It means from lighting strikes or switching operations, and designing protection systems to prevent equipment damage. And the physical condition of a conductor surface can have a significant electrical impact, especially at very high voltages. So we will have different impacts. So and such as corona discharge and so on. So corona discharge, a rough surface can create a high electric field gradient, causing the air surrounding the conductor to ionize. So this phenomenon, known as a corona discharge, so is visible as a faint glow and is accompanied by a hissing sound. So, and there are three primary parameters that model the electrical behavior of a transmission line: resistance, inductance, and capacitance. Okay, give me 5 minute time to have a break. Okay, if you have any questions, please let me know. Just 2 minute time for break, and then come back again. Okay, I come back again. If there is any questions, please ask me. Okay, this slide focus on two critical mechanical properties of overhead transmission lines, sag and tension. These properties are fundamental to the design, construction, and safe operation of the power grid, ensuring the physical integrity of the line and public safety. So sag is the vertical distance between the highest point of the transmission line conductor at the support towers and its lowest point in the span. It represents the downward curve of the conductor due to its own weight. Tension is the mechanical force or stress exerted on the conductor, pulling it taut between the two support towers. The interplay of sag and tension are inversely related to high tension, low sag. A conductor pulled very tightly, high tension will have less sag. So while this might seem desirable, it can create excessive mechanical stress on the conductor and the support towers, increasing the risk of mechanical failure, especially in windy conditions or under ice loading. So, to low tension or high sag, a conductor with low tension will have more sag. So, while this reduces mechanical stress, excessive sag can cause the conductor to come too close to the ground, buildings, or other structures, creating a significant safety hazard. So we have to find a compromise between these two criteria. So the analysis of sag and tension is a crucial part of the design process. Engineer must calculate and select the appropriate sag to ensure safety, structural integrity, and optimal span length. So understanding sag and tension is a primary responsibility for power system engineers to guarantee the reliability and safety of the electrical infrastructure. Okay, this slide addresses the critical concept of power flow and line loadability, which are central to operating a power system safely and efficiently. Understanding this concept helps us manage the grid capacity and prevent overloading, which can lead to instability and blackouts. Maximum power flow refers to the highest amount of power that a transmission line can safely carry without violating its operational limits. This is not a fixed value, but is a dynamic parameter that depends on the line's characteristics and the constraints of the system. So the primary goal of an operator is to ensure that the actual power flow remains below this maximum limit at all times. So line loadability is a measure of a line's capacity to transport power. This capacity is not constant and is influenced by the line's length. The primary limiting factor changes as the length of the line increases. We can categorize lines into three groups based on their length and corresponding limits. So for short line up to 80 kilometers, the main concern is the heating of the conductor. As current flows through the resistance of the line, it generates heat, Ri2 losses. If the current exceeds a certain threshold, the conductor can overheat, causing it to sag excessively or even melt. The thermal limit is the maximum current a conductor can carry continuously without exceeding its temperature rating. Another one, medium lines, 80 kilometer to 240 kilometer. Um, the inductance and capacitance of the line becomes more significant. These reactive components cause a voltage drop along the line. If the load is high, the voltage at the receiving end can drop to an unacceptable level, which can affect the performance of connected equipment. Therefore, the capacity of these lines is often limited by the need to maintain a stable voltage profile. Long lines or greater than 240 kilometer. For very long lines, the most critical issue is transient stability. A sudden disturbance such as a short circuit or a change in load can cause the generators at the sending and receiving end to lose synchronism with each other. If the system cannot recover quickly, it can lead to widespread power outages. The maximum power that can be transmitted is therefore limited by the system ability to maintain stability under these dynamic conditions. Understanding these different limits is crucial for planning and operating the power grid, ensuring that each line is utilized to its full potential without compromising system safety and reliability. Okay, this concluding slide summarizes the key takeaway from the presentation, looks ahead to the future of the power grid. So it's an opportunity to reinforce the main points and highlight the ongoing challenges and innovations in the field of power transmission. So the critical role of transmission throughout this presentation, we have explored the essential components of the power grid, transmission lines and cables. We have seen that they are for more than just wires. They are the critical arteries of our electrical infrastructures. Their design, including the choice between the overhead and underground, is a complex process that balance technical, economic, and environmental factors. Their operation requires a deep understanding of electrical parameters like resistance, inductance, and capacitance, as well as phenomena like the skin effect and the corona discharge. Their maintenance is vital for ensuring a reliable energy supply and involves sophisticated testing and fault location techniques. Um, the power grid is currently undergoing a massive transformation. The traditional model of large centralized power plants is evolving with the rise of renewable energy sources like solar and wind, and the increasing adoption of distributed generation, for example, rooftop solar panels. So the integration of these new sources makes the grid more complex and bidirectional. Power is no longer following in just one direction. So this new reality requires new technologies and materials to make the grid smarter, more resilient, and more efficient. And I need to find better ways to store energy, manage power flow, and protect against new types of faults. So the future of power transmission is not just about carrying power, it's about building a flexible and sustainable network that can meet the energy demands of tomorrow. So, following our my introduction to cables, I will delve into the following specific subjects: construction and classification. First, we will explore the fundamental aspects of cables. We will begin with general construction of cables and various insulating materials. So this will be followed by an overview of the classification of cables and a detailed look at the characteristics of both single core and multi-core cables. We will also touch upon the special case of superconductors. Next, we will focus on the more technical and analytical aspects. We will cover insulation and capacitance, how to calculate the insulation resistance and capacitance of a single core cable, and the concept of dielectric stress and its importance in cable designs will be presented. and determining the most economical conductor size in a cable, and the principle of cable grading will be explained here. And we will also discuss the cable effective resistance and the specific calculation for the capacitance of a three-core belted cable. Okay, we will begin by defining thermal resistance and then apply this concept to calculate the thermal resistance of the dielectric of a single core cable. Understanding this thermal characteristics is essential for determining a cable current rating and its permissible current loading, which directly affects how much power it can safely carry without overheating. So finally, we will examine the types of cable faults that can occur, which is a critical topic for maintenance and system reliability. This will provide a comprehensive overview of how cables behave under both normal and abnormal conditions. Based on this slide, which continues our introduction to power transmission, we can gain a more comprehensive understanding of underground cable by examining their additional advantages, key drawbacks, and typical applications. In addition to being less as susceptible to weather damage and require less maintenance, underground cables also have a smaller voltage drop compared to the overhead lines, which is beneficial for maintaining stable power delivery over shorter distances. Furthermore, they offer a significant aesthetic advantage, leading to a better general appearances as they do not clutter the landscape with towers and conductors. However, these benefits come with significant disadvantages. Their major drawbacks are the greater installation cost, which includes the expenses of trenching and specialized equipment, and installation problems they can introduce at high voltages compared to the simpler installation of overhead systems. Given this balance of pros and cons, underground cables are typically used in specific situations where the advantages outweigh the high cost and technical challenges. They are primarily deployed in locations where it is impractical to use over lines, such as in highly populated urban areas where municipal autostatic often prohibit the use of unsightly and space consuming overhead infrastructures. Okay, based on this slide, we can now understand the historical and modern applications of underground cables. For many years, the primary application of these cables was for the distribution of electric power in congested urban areas. They were predominantly used for lower and or moderate voltage applications, where the high installation costs and installation challenges at higher voltages were less of the concern. However, recent advancement is in both the design and manufacturing of cables have brought about a significant change. So these innovations have led to the deployment of robust cables that are now suitable for use at much higher voltages. So this technological progress has made it a viable option to use underground cables to not just for distribution but also for the transmission of electric power over short or moderate distances, particularly in situations where overhead lines are not feasible. This highlights how continuous improvements in power engineering have expanded the practical applications of existing technologies. So this slide provides a concise definition of an underground cable and explains the factors that determine its specific design. Essentially, an underground cable is composed of one or more conductors to carry the electric current, surrounded by suitable insulation to prevent electrical leakage and ensure safety. This entire assembly is enclosed within a protective cover that shields the cable from the mechanical damage and environmental factors once it's bored. It's important for students to understand that while this basic structure is universal, the exact type of cable used in any given application is not. The choice of cable depends heavily on two key factors: the working voltage, whether it's low, medium, or high voltage, and specific service requirements, which might include the amount of current it needs to carry, the environmental conditions it will face, and the equipped lifespan. Therefore, the design of a cable is a practical engineering decision tailored to its specific operational demands. So this slide outlines the fundamental requirements for the conductor used within a cable. In short, a cable conductor must be made of thinned standard copper or aluminum of high conductivity. The use of copper or aluminum is due to their excellent electric conductivity, which ensure minimal power losses during the transmission. So based on this slide, I want to discuss the key requirements that cable must fulfill to ensure safe and reliable operation. First, the conductor size must be carefully chosen to meet two crucial criteria. It must be large enough to carry the desired load current without overheating and to keep the voltage drop within permissible limits. Overheating can damage the cable, while excessive voltage drop leads to inefficient power delivery. Second, the cable must have a proper thickness of insulation. This is a direct measure of safety and reliability, as thicker insulation provides greater protection against electrical leakage and short circuit, particularly at higher voltage for which the cable is designed. Finally, to withstand the stress of insulation and a long service life, the cable must be provided with suitable mechanical protection, and the material used in its construction must have complete chemical and physical suitability throughout. So these requirements ensure the cable remains intact and performs reliability under various operational and environmental conditions. Okay, it's examine the construction of a three-core cable as shown in the figure. This type of cable is made of multiple layers, each serving a specific purpose to ensure safe and reliable power transmission. So the main component of a three-core cable are conductor, paper insulator, lead sheets, batting, armoring, and servings. You can see in this figure. So based on this slide, we can summarize the various parts of the standard underground cable, including cores or conductors, which are the actual wires that carry the electric current, insulations, a metal shield surrounds the insulations. Bedding serves as a protective cushion for these shields, and armoring, typically a layer of steel, provides vital mechanical protections against external impacts, and serving, which protects the armoring from corrosion and wears. So this slide explains the fundamental component of cable, the core or conductor. A cable can be designed with either a single core or multiple cores with a number of conductors directly depending on the type of service it's intended for. For example, a three conductor cable is especially used for three-phase power services and so on. Okay, this slide explains the essential role of insulation in cable design. The core principle is that each conductor must be covered with a suitable thickness of insulation. So this is very essential for all of cables. Based on this slide, we can delve into the crucial function of the metallic shields in cable construction. A metallic shield typically made of lead or aluminum is placed directly over the insulation layer, and it can protect moisture and gases. Purpose of the beading layer in a cable's construction is a layer of fibrous material such as jute or hisen type that is applied directly over the metallic sheets. And its primary function is to protect the shields in two crucial ways. First, in safeguard the metallic layer against corrosion, and the second, it acts as a mechanical caution to prevent injury from the armoring layer. So armoring layer, over the beading, a layer of armoring is applied, which typically consists of one or two layers of galvanized steel wire or steel type. Its primary purpose is to provide robust mechanical protection to the cables. Based on this slide, we can now discuss the final layer, which is a saving layer. So this is the outmost layer consisting of fibrous material like jute, similar to the beading layer we discussed earlier. Its purpose is to provide a final protective coating over the armoring. Okay, based on this slide, I discussed the critical properties required for the suitable cable insulating material. The satisfactory operation of a cable is highly depending on its insulation, which must meet several key requirements. First and foremost, it must have a high dielectric strength to prevent the electrical breakdown of the cable and high insulation resistance to avoid leakage currents. From a physical and chemical standpoint, the material needs high mechanical strength to withstand the rigors of handling and insulation, and it must be immune to chemical attacks from acid and alkalis over a wide range of temperature. So based on this slide, we will discuss another crucial property of insulation materials, beading hygroscopic. This term simply means that the material should not absorb moisture from the air or soil. So this is also very important. Based on this slide, we can now discuss a practical engineering principle regarding the insulating material. As the slide pointed out, no single insulating material possesses all the ideal properties that we discussed previously. This means that a key decision must be made during the decision process. Therefore, the type of insulating material to be used in a cable depends on two critical factors: the purpose for which the cable is required and the quality of insulation to be aimed at. So based on this slide, we will discuss the principal insulating materials used in the construction of cables. The selection of material is critical engineering decisions as it must provide the required electrical and physical properties for specific applications. Some of the most common materials used include traditional options like rubber and vulcanized India rubber, which were popular for their flexibility, and Impregnated paper saturated with oil has long been a standard for high voltage cables due to its excellent dielectric strength, and uh, varnish cambric is another option, through less common today. In modern applications, PVC is a very popular and cost-effective choice for low and medium voltage cables, and XLP is a widely used material due to its superior thermal and electrical properties. So this slide provides an in-depth look at rubber as a potential insulating materials, highlighting both its capabilities and limitations. While rubber poses reasonably high insulating properties with a relative permittivity of 2 to 3, a dielectric strength of about 30 kilovolt per millimeter, and an insulation resistivity of 10 times 1017 ohm centimeter. It has several major drawbacks. It readily absorbs moistures and has a very low maximum safe operation temperature of about 38 degrees centigrade, which makes it unsuitable for most power applications. Furthermore, rubber is soft and liable to damage from rough handling and edges when exposed to light, which compromise its long-term reliability. So this is like explain the properties of vulcanized India rubber, a key insulating material. VIR is a compound created by mixing pure rubber with material matter, which then undergoes a process called vulcanization. This process gives VIR greater mechanical strength compared to pure rubber, making it more durable. So this slide explains the properties of impregnated proper as an insulating material, a type of insulation that has almost entirely supersede the rubber insulation due to its superior properties. Its primary advantages are low cost, low capacitance, and both high dielectric strength and high insulation resistance. The main drawbacks of paper, however, is that it is hygroscopic. This means that it can absorb moisture, which then lowers its insulation resistance, even if it is integrated with a compound. So based on this slide, we will discuss varnish cambric, another material used for cable insulation. This material is essentially a cotton cloth impregnated and coated with varnish, and is also commonly known as empire tape. Okay, based on this slide, we will discuss PVC, a common synthetic insulating material. PVC is a synthetic compound that is supplied in the form of white powder. It is widely used for cable insulation because it possesses excellent electrical and physical properties over a wide range of temperatures. So based on this slide, we can further analyze the properties and specialization of PVC insulation. A key advantage of PVC is that it is inert to oxygen and nearly inert to a variety of alkalis and acids. Due to this chemical interness, it is often the preferred choice over VIR for use in extreme environmental conditions, such as those encountered in cement or chemical factories. Based on this slide, we can now discuss cross-link polyethylene, commonly known as XLPA. So this material is classified as a thermoset insulation material. The key to its properties lies in the process of cross-linking, which changes the molecular structure of the polymer change, binding them more tightly together. So based on this slide, we will discuss the properties of PE, polyethylene, and the reason for creating cross-link polyethylene or XLPE. Polyethylene as a material has excellent electrical properties, including high insulation resistance, excellent dielectric strength, and a low dissipation factor across all frequencies, which would make it an ideal insulator. However, its use is limited in its temperature range. To overcome this limitation, the PE is cross-linked to form XLP, a process which significantly increases the temperature range of the insulation while maintaining its superior electrical properties. So based on this slide, we will discuss how underground cables are classified. So cables are generally classified into two ways, either by the type of insulating material used or by the voltage for which they are manufactured. The latter method, based on the voltage, is generally preferred. So according to this classification, cable can be divided into distinct groups based on their operating voltage range. Low tension or LT cables are used up to 1000 volts. High tension cables are rated up to 11 kV, and super tension cables operate from 22 kilovolt to 33 kilovolt. For even higher power transmission, there are extra high tension cables which handle voltages from 33 kilovolt to 66 kilovolt. And finally, extra super voltage cables are used for voltages beyond 132 kilovolt. So this slide explained that underground cables can be designed with different numbers of cross depending on the service requirement. A cable may be single core, two core, three core, or four core, and so on. The number of cores is selected based on the types of electrical system and the nature of the load being supplied. This slide explains cable selection for three-phase systems. For a three-phase service, either three separate single core cables or one three core cables can be used. The choose depends mainly on the operating voltage and the load demand. Each option has its own advantages in terms of installation, cost, and performance. So this slide provides further details on the design and characteristics of single core cables. For voltages up to 6.6 kilovolt, the electrical stress are low, eliminating the need for a special construction to control the electric field or thermal conductivity. So structurally, these cables feature a core with circular section, and all layers of insulation and protection are arranged concentrically around it. So a key design difference is that single core cables are typically not armored to prevent excessive shield losses. The principal advantage of this type of cable are its simple construction and the ability to use a larger Cooper section for the conductor. Based on this slide, we will discuss the characteristics and application of multi-core cables in practice. Underground cables are most often used deliver three-phase power. For this purpose, engineers have the option of using either a single three-core cable or three individual single-core cables. So we will discuss the different types of cables in this slide, generally used for three-phase services, categorized by their voltage applications. For voltages up to 11 kV, belted cables are typically used, and for cables 22 to 66 kilovolt, screen cables are the standard choice. Finally, for cable above 66 kilovolt, pressure cables are used. So based on this slide, Belted cables are a type of three-core cables used for voltage up to 11 kV and occasionally up to 22 kilovolt in specific cases. Okay, this slide explains the limitation of the belted cables and the necessity of using screen cables for higher voltages. For voltages below 22 kilovolt, the electrostatic stress within the cable insulations are primarily radial, meaning that they act across the thickness of the insulation. This makes belted cable construction suitable for low and medium voltages. Screen cables are a type of cable designed for a specific voltage range. They can be used for voltages up to 33 kilovolts, and the, there are two main types of screen cables: H-type cables and SL-type cables. So based on this case, well, this slide, we will discuss the construction of typical H-type screen cables. So H-type cable structure, starting from the inside, each of the three conductors is insulated with paper insulation, and then individually covered with a metallic screen. These screens are an essential feature of screen cables, as they are designed to conduct leakage currents to the ground, preventing them from causing local heating and insulation damage. So the three screen cores are then enclosed within the conducting build, and the entire assembly is surrounded by a lead sheets to protect to it from moisture. So we can see the H-type cables in this slide. This detailed diagram illustrates how the layers of two separate cables are connected to form a continuous joint. So the most critical aspect of the H-type cable construction is the metallic screen around each individual one's core, which is visible in this figure. So this slide explains the advanced construction and electrical principle of H-type cables, which are a type of screen cable. So each core of an H-type cable is insulated with layers of impregnated paper, and is then covered with an individual metallic screen, which is usually a perforated aluminum foil. These screens on each core are laid so so that they make contact with one another. An additional conducting belt is wrapped around the three cores. So unlike belted cables, H-type cables have no insulating belt. Instead, they have a lead sheet. The three core screens, the conducting belt, and the lead sheets are all at earth potential. This arrangement ensures that the electrical stress within the cable are purely radial, meaning that they only act across the thickness of the insulation, thereby reducing the electric losses. The presence of the metallic screens and the conducting belt helps prevent undergoes tangential stress that cause insulation breakdown in the belted cable at high voltage. Okay, this is a this is like showing the SL type cables, which are another kind of screen cable. The key difference in the construction is that each of the three cores is insulated and then covered with its own separate lead sheets. Okay, this slide lists two principal advantages of um, H-type cable. Um, so let me. Okay. Sorry to drink some water. Just here. Okay. Um, this slide listed two principal advantages of H-type cables. Disadvantages are directly related to their specialized construction, which is designed to handle high voltage efficiency. So, um, and advantages of H-type cables first are designed to eliminate the possibility of air pockets or voids within the deleting insulation. These voids are problematic because they tend to significantly reduce the cable's breakdown strength and can cause serious damage to the proper paper insulation. By preventing them, the cable reliability and uh, longevity are improved. Second, the metallic screens that are a key feature of the H-type cables also increase the heat dissipating power of the cable. This improves uh, the the performance, thermal performance allows the cable to operate more efficiently and handle higher current load without overheating. Okay, uh, this slide. Um, okay, let me. This slide discuss the limitation of the solid type cables. This category includes all the cables previously discussed that use solid insulation such as a belted cable because they do not have a gas or oil circulating within the cable sheets. The primary limitation of these cables is their voltage capacity. They are only suitable for voltage up to 66 kilovolt. Uh, and this slide introduced the pressure cables, which are designed. Sorry, I explained about this. So, uh, pressure cables, which are designed for high voltage applications. As we have seen, solid types cables are not reliable for voltage behind 66 kilovolt because of the danger of insulation breakdown caused by the presence of voids. So to solve these problems, pressure cables are used for operating voltages greater than 66 kilovolts. These cables eliminate voids by maintaining high pressure on the insulating compound, which is where their name comes from. So this slide also notes that there are two main types of pressure cables: oil field cables and gas pressures. All right. This slide provides a detail on oil field cables, which are a type of pressure cable designed for high voltage applications. The main feature of these cables is the inclusion of channels or ducts or for the circulation of oil. This oil is kept under pressure by external reservoirs and is constantly supplied to the channels. The pressure oil serves critical purposes it compresses the layer of paper insulation and is forced into any voids that may have formed within the cable. Because this design effectively eliminates voids, oil filter field cables can be reliably used for higher voltages, especially in the range of 66 kilovolt up to 200 kilovolt. Okay, this slide displayed a cross-sectional view of a single core conductor channel, oil field cable in a diagram labeled figure 11.6. As the name suggests, this cable has a central oil duct. Surrounding this duct are the conductors, followed by layers of paper insulation and lead sheets. The outer uh, layers of the cable include beading and severing. This construction allows pressurized oil to circulate through the central duct, which compresses the insulation and fills any voids that may form. So this is crucial for preventing insulation breakdown at high voltage. So this slide displayed a cross-sectional view of a single core shield channel oil field cable. Unlike the conductor channel type, where the oil duct is at the center, this cable features groove shields with oil channels embedded in it. So from the center outward, the cable consists of a single conductor which is surrounded by paper insulation. The paper insulation is in turn covered by groove shields. The grooves in the shields from the oil channels, which are kept filled with pressurized oil. This pressurized oil compresses the insulation and fills any voids that may form, thereby preventing insulation breakdown at high voltage. All right. This slide illustrates a cross section of a three-core filler space channel oil field cable. Unlike the previous single core design, this cable has three separate coils laid together. So this figure shows that the empty space between the three insulated cores and the outer lead shields are used as oil duct. This design allows the pressurized oil to circulate through these filler space channels, compressing the paper insulation and filling any voids that may form, which is crucial for preventing insulation breakdown at each voltages. Okay, this slide outlines the primary advantages and disadvantages of oil field cables. The main advantages of these cables are directly related to their use of pressurized oil. First, the high pressure oil successfully avoids the formation of voids and ionization within the cable's insulation, which are major cases of cable failures. So this allows the cable to operate with a higher dielectric strength and over a wider temperature range. Second, the system provides a safety feature. If there is a leak in the lead sheets, it is immediately detected, which reduces the chance of earth fault. Despite their performance benefits, oil field cables have significant drawbacks. Their primary disadvantages are their high initial cost and the complicated system required for laying them. All right. Uh, the slide explained the details. Sorry, there is a problem again in my. Okay, let me check again. I don't know what's happened for my PowerPoint. So this slide explains the details of gas pressure cables. These cables are a type of pressure cable used for high voltages, as solid type cables are unreliable for voltages above 66 kilovolt. So as shown in this figure, these cables consist of three cores, each individually insulated. These three cores are placed inside a gas-tight steel pipe. The space inside this pipe is filled with dry nitrogen gas at high pressure, typically between 12 to 15 atmospheres. The main purpose of this design is to eliminate voids, air pockets inside the cable. Voids can significantly reduce the insulation strength and cause cable failure at high voltages. By keeping the cable under high gas pressure, these voids are compressed and eliminated, making the cable suitable for very high voltages. Okay, this slide explains the details of gas pressure cables. These cables are a type of pressure cable used for high voltages, as solid type cables are unreliable for voltages above 66 kilovolt. Construction of as shown in this slide, this cable consists of three cores, each individually insulated. These three cores are placed inside a gas-tight steel pipe. The space inside this pipe is filled with dry nitrogen gas at a high pressure, typically between 12 to 15 atmospheres. So, uh, excuse me, give me a second to. Yes, this one. Um, so based on the information provided in this slide, here is a detailed explanation of high temperature superconductivity, superconducting cables for you. HTS, so cables um represent actually HTS cables represent a significant advantage in electrical power transmission. These cables, which have been in development for some time with key milestones achieved around 2012, offer several compelling advantages over conventional copper or aluminum cables. So one of the defining characteristics of HDS cables is their ability to transmit a much greater amount of power, um, specifically 3 to 5 times to the power of the traditional cable of a similar size. This is due to their superconducting properties, which allow electricity to follow with visually no resistance when cooled to a specific temperatures. Okay, based on the provided slide, here is a detailed explanation of superconducting transformers for you. Superconducting materials are not only revolutionary power cables, but are also being applied to other critical components of the electrical grid, such as transformers. As indicated in this slide, this material can be used to replace the traditional copper windings found in conventional transformers. Okay, based on this slide, here um, So, insulation resistance is a crucial property of an electrical cable. representing the opposition offered by the insulating material to the flow of leakage current. So to ensure safe and efficient operation, a cable conductor is encased in a layer of insulating material of a specific thickness. So the purpose of this insulation is to prevent any unwanted current from escaping the conductor. When a small amount of current does manage to escape, it is referred to as leakage current, and its path is typically radial, following from the conductor outward through the insulating layer. So this figure illustrates the cross section of a single core cable, a fundamental component in power transmission. The innermost circle with a radius denoted as R1 represent the cable conductor, the core that carries the electrical current. Surrounding the conductor is a thick layer of insulating material which extends radially outward to a radius of R2, known as an internal sheath radius. The primary purpose of this insulating layer is to prevent the flow of unwanted leakage current. And this figure also shows an uh, intentional small cylindrical shell of insulation at a radius x with a thickness of dx. So this elemental shield is included to help in the mathematical calculation of the total insulation resistance. By considering this small element, you can use integral calculus to determine the overall opposition to the radial flow of current through the entire insulating layer, value that must be very high for the cable safe and effective operations. Okay, based on this, so we will have some parameters like this. L be length of the cable, and rho is the resistivity of insulation, considering a very small layer of insulation of thickness of dx at a radius x. So and the area of cross-sectional section offered to this follow is 2p times x L. So the final slide presents a mathematical derivation for calculating the insulation resistance of a single core cable. So the purpose begins by considering a cylindrical layer of insulation at radius x with a thickness of dx. The insulation resistance for this tiny layer, denoted as a dr, is given by the formula. Dr is equal to rho a dx, where rho is the resistivity of insulation material and a is the area through which the leakage current flows. In this specific geometry, the leakage current flows radially outward, and in cross-sectional area it encounters is the surface area of the cylindrical layer, which is A is equal to 2p times L. Therefore, the resistance of the elemental layer is expressed as dr is equal to rho over 2pl times log r2 over r. So to find the total insulation resistance of the entire cable, we must integrate this expression from the inner radius R1 of the conductor to the outer radius, or R2 of the insulation. So here we have present a practical example of calculating the insulation resistance of a single core cable based on its physical dimensions and material properties. The conductor diameter is given as 1 centimeter, leading to a conductor radius of 0.5 centimeter, while the insulation thickness of 0.4 centimeter results in an inner radius of zero point 0.9 centimeter. The cable length is 2 kilometer, and the insulation resistivity is provided is in ohm centimeter, which is carefully converted into ohm meter for consistency in SI units. So the solution applies the standard formula for insulation resistance of cylindrical cable, showing how resistance depends logarithmically on the ratio of outer to inner radius, as well as directly on the resistivity and inversely on the cable length. So we just need to substitute all of given values, and we can calculate easily the insulation resistance. This is another example demonstrate how to determine the insulation thickness of a single core cable when the insulation resistance, conductor size, and material resistivity are known. The given data includes a cable length of 1 kilometer and insulation resistance of 495 mega ohm, conductor diameter of 2.5 centimeter, yielding a radius of 1.25 centimeter, and insulation resistivity expressed in ohm centimeter, which is converted into ohm meter for consistency. The unknown parameter is the outer radius of insulation from which the thickness can be derived. So we can use again this formulation. So by arranging this standard insulation resistance formula, the ratio of outer radius to the inner radius can be calculated using algorithm relationships. So we can find this uh, algorithms, and finally we just need to replace the values, and we can find R2, and then insulation thickness is equal to R2 minus R1, which is equal to 1.25 centimeter. So this is another slide, another example, practical example of determining the resistivity of the insulating material in the single core cable. Again, we can use these equations. We just need to find the resistivity of insulating material. So rho is unknown parameters. So by just substituting the given values, we can find the rho here. So this slide is representing the um, uh, this slide complete the actually capacitance of the single core cables. So again, we have these single core cables, and we want to find the capacitance of this single core cable. So here uh, we have Q is the charge per meter actual length of the cable in coulombs, and E be permeability of the insulation material between uh, core and lead sheets, and uh, the derivation starts with the definition of capacitance. So C is equal to Q over V. So, and also E is equal to E0 times ER. ER is the relative permeability of insulation. So, and here uh, we have these equations to find the electric intensity at point P. So in order to find these equations, this formula, we need to first find the surface area of this cylinder, which is equal to 2px meter square, and then we can calculate the electric flux density at point P, which can be simplified based on these equations, and then by replacing the values we can find these final equations. All right. Uh, so the voltage of between the conductor and shields also can be calculated based on the integration of the this electric intensity at point P. Finally, we will have these equations for voltage between the potential difference voltage between the conductor and shields. Uh, this slide completes the mathematical derivations for the capacitance of a single core cable. The derivation starts with the definition of capacitance. C is equal to Q over V. So where Q is the charge per meter length of the cable and V is the potential difference between the conductor and sheets. By substituting the previous derived expression for the potential differences, so we can find finally C is equal to these equations. And in addition to resistance, cables also have capacitance, which is a key consideration in AC power systems. As I told you, a single core cable can be modeled as two coaxial cylinders, the inner conductor and the outer lead sheets with the insulation acting as the dielectric. This creates a capacitor causing a charging current to follow. The capacitance is a function of the cable's geometry and the permeability of the insulating materials, epsilon R. The final formula for a cable with length L is given by C is equal to this equation, where D and capital D and small d are the outer and inner diameters respectively. This relationship helps you calculate the charging current and analyze the overall electrical behavior of the power systems. So here we have one example. This is a practical example illustrating how to apply the capacitance formula to a real cable. A single core cable is considered where the conductor diameter and the inner shield diameter define the geometric ratio d over d, and the insulating material is characterized by its relative permeability. By substituting the given values, epsilon r is equal to 4, cable length L is equal to 1000 meters, and the diameter ratio into the standard capacitance equation, the total capacitance can be calculated step by step by using of this equation. So the result shows that just we need to uh, replace the given values. The result shows that the capacitance for 1 kilometer length of the cable is approximately 0.378 microfarad. This example highlights how both the physical dimensions and the dielectric properties directly influence the cable's ability to store charge, and it demonstrates a straightforward method engineers use in cable design and performance evaluations. So this is another example. So this is a practical example of calculating a capacitance and charging current of a single core cable used in three-phase 66 kilovolt power system. The cable has a length of 1 kilometer, a core diameter of 10 centimeter, and an insulation thickness of 7 centimeter with a relative permeability of 4. The capacitance is determined based on the geometric dimensions of the cable and the electric property of the insulation. The governing relation used in this calculations again can be calculated based on this equation. So by substituting the given values, the capacitance of cable can be obtained to this value 0.254 microfarad. Then proceed to calculate the phase voltage, considering the line voltage is 66. So this is in the three-phase systems. We can find the phase voltage approximately 38.1 kilovolt between the core and shields. Using this voltage and the capacity reactance relationship, the charging current can be calculated. Finally, the charging current can be found to be 3.04 amp, highlighting the effect of cable capacitance in AC systems, especially over long distance. This example clearly demonstrates how physical dimensions and material properties influence the electrical performance of a power cable. So this slide illustrates a comprehensive example of determining the capacitance, charging current per phase, and total charging reactive power of a three-phase underground cable system operating at 33 kilovolt and 50 hertz. The system consists of three single core cables, each 4 kilometers long, with a conductor diameter of 2.5 centimeter and insulation thickness of 0.5 centimeter. Using the given relative permittivity of 3, the capacitance per phase can be calculated based on the cable's geometric and dielectric properties. The governing relations, we can use again this equation. So by substituting the given value, we can find the capacitance, and then voltage phase can be easily found based on the voltage lines. And then charging current also can be, this is Ohm law, charging current per phase is equal to voltage divided by impedance. And total charging kilovolt amp in three phase should be multiplied to 3V phase IC. This is equal to apparent power. So this slide introduced the concept of the dielectric stress in a single core cable, which is a crucial factor in cable insulation design and performance. Under normal operation conditions, the insulation surrounding the conductor is subject to electrostatic forces due to the applied voltage. This phenomenon is referred to as the dielectric stress. In practical terms, dielectric stress represents the electric field intensity within the insulation and is directly related to the potential gradient at any point within the between the conductor and the shields. It is important to note that this stress is not uniformly distributed, and instead it is highest at the surface of the conductor and decreases as the distance from the conductor increases toward the outer sheets. So understanding the dielectric stress is essential for showing that the insulation material can withstand these electric forces without breakdown, thereby maintaining the reliability and safety of the cable systems. So this slide develops the analytical expression for electric stress within a single core cable by considering its geometric structure. The cable is designed by a core of diameter D and an internal shields of diameter D, forming a cylindrical insulation region between them. So based on electrostatic field theory, the electric intensity at any point located at a radial distance x from the center of the cable can be expressed by these equations. This equation E is equal to Q over these values. So this relation shows that the electric field and hence the dielectric stress is inversely proportional to this form of conductor center. As a result, the stress is maximum at the surface of the conductor, where X is minimum, and gradually decreases toward the shields. So this non-uniform distribution of electric stress is a key consideration in cable design, as it influences insulation thickness, material selection, and overall reliability of the cable under high voltage conditions. In a single core cable, the potential difference V between the conductor and the shield is given by this equation. So where Q is the charge per unit length, epsilon R 0 is the permeability of the free space, epsilon R is the relative permeability of the insulation, D is the conductor diameter, and capital D is the internal diameter of the shield. From the expression, the charge per unit length can be determined by this equation. Using this result, the potential gradient electric field intensity at a distance x from the cable center is obtained based on this equation. So this shows that the dielectric stress is inversely proportional to the radial distance x. The maximum electric stress occurs at the surface of the conductor. It means at x is equal to a small d over 2. This is a maximum value. So G maximum will be like this. So similarly, the minimum dielectric stress occurs at the inner surface of the shields. It means X is equal to capital D over 2, giving this value. G minimum is equal to this one. So it is therefore clear that the dielectric stress is not uniformly distributed across this insulation. It is highest at the conductor surface and gradually decreases toward the shields. So this non-uniform distribution is an important consideration in cable design, since the insulation near the conductor must withstand the highest electrical stress. To improve performance and reduce the risk of insulation failure, you often employ insulation grading techniques. So in summary, the dielectric stress in a single core cable is a maximum at the conductor surface and minimum at the shields, which is a fundamental principle in the design of HV power cables. So the ratio of maximum to minimum dielectric stress in a single core cable is an important parameter for understanding how the dielectric field is distributed across the insulation. From the previously desired expressions, the maximum dielectric stress occurs at the conductor surface is given by G max, while the minimum stress occurs at the shield surface and is given by G min. So the result shows that the stress ratio depends only on the geometric ratio of the shield's diameter to the conductor diameter, and depends of the applied voltage and the permeability of the insulating material. So in practice, a larger value of the D over D leads to a greater difference between the maximum minimum stress, indicating a more non-uniform electric field distribution across the insulations. So therefore, in cable design, the ratio D over D must be carefully selected to limit stress concentration at the conductor surface and to ensure reliable and safe insulation performance. So this slide explains how the dielectric stress or electric stress varies within the insulation of the cable. So this figure shows that the dielectric stress is not uniform through the insulation, and instead the stress is highest at the conductor surface and decreases as we move outward toward the sheets. This happens because the electric field strength is inversely proportional to the distance from the conductor. The maximum stress occurs right at the conductor surface, and this is a very important factor in cable design. If the insulation is not able to withstand this maximum stress, the cable will fail, even if the average stress across the insulation seems acceptable. For example, suppose a cable is operating at a voltage where the maximum dielectric stress at the conductor surface reaches 5 kilovolt per millimeter. In that case, the insulation material must have a dielectric strength of at least 5 kilovolt per millimeter to avoid breakdown. Otherwise, electrical failure, insulation breakdown will occur. In short, when designing or choosing insulation for cables, you must always consider the maximum dielectric stress rather than the average stress. This ensures safety, reliability, and longer lifespan for a cable. This slide presents an example of electric stress distribution in a single core cable operating at 33 kilovolt. The cable has a conductor diameter of 1 centimeter and an internal shield diameter of 4 centimeter. The analysis focuses on determining the maximum and minimum electric stress within the insulation. The maximum stress occurs at the surface of the conductor and is calculated using the logarithmic relationship between the shields and conductor diameters. So resulting in a value of approximately 47.61 kilovolt per centimeter RMS value. In contrast, the minimum stress appears at the inner surface of the shields where the electric field is weakest and is found to be about 11.9 kilovolt per centimeter. So these values can also be derived proportionally from the maximum stress using the ratio of conductor to shield diameter. Overall, the example highlights how electric stress is non-uniformly distributed across cable insulation, being highest near the conductor and decreasing toward the inner shields, which is a critical consideration in the cable design and installation reliability. Okay, this is another example. This example also explain how to determine both the insulation thickness and operating voltage of a single core cable based on given electric stress limits. The maximum and minimum dielectric stresses are provided as 40 kilovolt per centimeter and 10 kilovolt per centimeter respectively, with a conductor diameter of 2 centimeter. Using the relationship between maximum and minimum stress, the shield diameter is calculated to be 8 centimeter. From this, the insulation thickness is obtained as 3 centimeters, showing how the geometry of the cable directly depends on the allowable stress levels. The second part of the example focuses on finding the operating voltage by applying the standard equation for maximum electric stress in a cable and substituting the known values. The operating voltage is determined to be approximately 55.45 kilovolt. Overall, this example demonstrates the practical application of electric stress relationships in cable design, linking physical dimensions with electrical performance to ensure safe and efficient operation. Uh, this slide present a comprehensive example of analyzing a single core cable operating on an 11 kilovolt 50 hertz system focusing on electric stress and key electrical parameters. So the conductor has a cross-sectional area of 0.645 centimeter cube centimeter, from which the conductor diameter is calculated as approximately 0.906 centimeter, while the internal sheath diameter is given as 2.18 centimeter. Using these dimensions, the maximum electrostatic stress is determined at the conductor surface, yielding a value of about 27.65 kilovolt per centimeter RMS, which represent the highest electric field intensity within the insulation. Conversely, the minimum electrostatic stress occurs at the shields and is calculated as approximately 11.5 kilovolt per centimeter, indicating the non-uniform distribution of the electric field across the dielectric. This example highlights how cable geometry and material properties such as permittivity influence stress levels, which are critical for insulation design, reliability, and preventing dielectric breakdown in power cable systems. This slide explains how to calculate the capacitance of a cable and its corresponding charging current. The capacitance C depends on the relative permeability of the insulation, epsilon r, the cable length L, and the ratio of conductor spacing to conductor diameter, D over small letter d. By substituting the given values, the capacitance can be calculated using the logarithmic expression, resulting in approximately 0.22 microfarad. This highlights how insulation properties and geometric configuration influence the cable's ability to store electric charge. So the second part of the slide focus on the charging current, which rises due to the cable capacitance when an AC voltage is applied. So using the relation IC is equal to 2P FCV, where F the supply frequency and V is the operating voltage, the charging current can be determined to be 0.76 amperes. So this demonstrates that even in the absence of load, underground or long cables draw a capacitive current, which is an important consideration in power system design, especially for voltage regulation and reactive power management. All right, let me just drink some water. This slide discuss the concept of most economical conductor size in a cable, which is determined by a specific relationship between the conductor diameter and the internal sheath diameter. The key point of this slide are as follows. So maximum stress location, the maximum electrostatic stress or G maximum in a cable occurs at the surface of the conductor. This is a critical design parameter as the electric strength of the insulation must be greater than this maximum stress for the safe operation of the cable. So the maximum stress is given by the formula, this formula, and to determine the most economical conductor size, the values for voltage V and the internal sheath diameter D are considered fixed due to the design requirements. This leaves the conductor diameter D, small d, as the only variable in the equation for maximum stress. So the most economic conductor diameter is the one that results in the minimum possible value for maximum stress, G maximum. So this is because a lower maximum stress allows for less insulation materials, reducing the overall cost of the cable. To find the value of the D, this D, small letter d, that minimize G maximums, the denominator of the stress equations, so we can derive the equation must be maximized. So this is achieved by taking the derivative of the denominator with respect to d and setting it to 0. So the calculation involves the product role of differentiation, so is equal to 0. And finally, uh, we can conclude that for the most economical conductor size, the ratio of the internal sheath diameter to the conductor diameter should be equal to the base of the natural algorithm Neper, Neper value, which is approximately, or Euler value. Approximately is equal to 2.718. So this ratio is known as Kelvin law for cable design. So this slide reiterates the key finding that the most economical conductor diameter D is given by this formula. So this value of D minimize the maximum electrostatic stress G max for fixed values of working value voltages V and internal sheath diameter D. Under this condition, the minimum value of G max is given by G max is equal to T 2V divided by D. So this slide then addresses the practical limitation of applying this theoretical formula to different types of cables. For uh, low and medium voltage, yes, for low and medium voltage cables, for these cables, the conductor diameter calculated using the economical formula, D is equal to 2V G max, is often too small. So this can result in a high current density, which can lead to overheating and potential damage. Therefore, for low and medium voltage cables, the conductor diameter is determined primarily by the consideration of safe current density. So rather than minimizing stress. So for higher voltage cable, in contrast, for the theoretical formula yields a very large conductor diameter D to minimize the stress. So this diameter is often much larger than what's needed for current carrying capacity alone. Therefore, it is advantageous to increase the conductor diameter to this value. So, okay. Uh, this uh, slide lists 4 methods to increase the conductor diameter of a cable without using an excessive amount of copper, primarily for HV applications where a larger diameter is needed to reduce electrical stress. So first of all, aluminum has a higher resistivity than copper. So for the same current carrying capacity, an aluminum conductor needs to have a larger diameter. Using the copper wires standard around the central hemp core. So by using of a non-conductive lightweight material like hemp as a central filler, the copper wires are forced to form a larger overall conductor diameter. This increases the diameter for electrical stress purposes without significantly increases the amount of copper. And another method is using a central lead tube instead of hemp. So similar to the hemp core method, a lead tube can be used as a non-conductive filler to increase the overall diameter of the cable. Another method is using a cable with a hollow core and a cooling medium. This advanced method uses a hollow core through which cooling medium such as water or oil can follow. This diagram increases the effective diameter of the conductor while also providing significant advantages in terms of heat dissipation. The improved cooling allows for higher current rating for the cable, making it more efficient. So this is another examples. Uh, Based on this example, we want to find the most economical value of diameter of a single core cable to be used on 50 kilovolt single phase system. So we have 50 kilovolts, so we can find easily natural voltage phase. So by multiplying to square 2, so maximum permissible stress, G maximum is 40 kilovolt. So G max is equal to 2V over T D. We want to find the D here. So D can be simply find 3.53 centimeter. This is another example. Find the most economical size of a single core cable working on 132 kilovolt three-phase systems. If a dielectric stress of 60 kilovolt per centimeter can be allowed, so again, phase voltage of cable can be calculated based on this. So this is peak value of phase voltage. This is RMS value, so peak value can be calculated based on this. Geomax D can be calculated based on this equation. And finally, internal diameter of shield D is equal to Euler value times D. So we can find this value. So this example demonstrates how electrical stress limitations directly influence cable dimensions and help engineers achieve a safe and cost-effective insulation design. So uh, the, this slide is explaining about the cable grading. Cable grading is a process of achieving more uniform electrostatic stress within the dielectric insulation of a cable. In an ungraded cable, the electrical stress is highest at the conductor surface and decreases as you move outward toward the shield. This non-uniform stress distribution can lead to insulation breakdown. Grading helps to mitigate this issue. And we have capacitance grading is a technique used in high voltage cables to achieve a more uniform dielectric stress across in the insulation. This is accomplished by replacing the single homogeneous dielectric material with composite dielectric. So the composite dielectric consists of multiple layers of different insulating materials. These materials are chosen and arranged in a specific way. The relative permeability epsilon r of each layer is inversely proportional to its distance from the center of the cable. This means that the layer closest to the conductor has the highest permeability, and the layer further out have progressively lower permeability. So we have this first equation represent the electric field strength E at a radial distance x from the center of the cylindrical cable conductor. We already discussed about all of these parameters. So this slide explains the key concept behind capacitance grading to make the electric field uniform and constant throughout the dielectric. To achieve this, the relative permeability epsilon r is made to vary with the radial distance x in a specific way. So the condition for uniform stress is that the relative permeability epsilon r must be inversely proportional to the distance from the center x. This relationship is expressed as epsilon r is proportional to 1 over x. So by substituting the inverse relationship of epsilon r into the original formula of E, we can find this value, this equation. So the final expression for E shows that it is a constant value independent of the radial distance x. This proves that by using a dielectric material whose permittivity decreases with distance from the conductor, uniform electrostatic stress can be achieved across the insulation. This is the fundamental principle of capacitance grading. So this slide represents an example of electric stress analysis in a 100 kilovolt single core lead shields cable with graded insulation. The conductor has a radius of 1 centimeter, while the internal sheath radius is 4 centimeter. The insulation is divided into two electric regions. The first radial layer of 1 centimeter thickness has a higher relative permeability of 5, and the remaining insulation has a relative permeability of 3. The objective is to determine the maximum and minimum electric stress in electric dielectric layer. Because the dielectric constants are different, the electric field distribution will not be uniform, and the stress changes at the boundary between the two materials. The inner layer with a higher permeability helps reduce the maximum stress near the conductor surface, where electric stress is usually highest. After calculating the stress value, the results are compared with those of the cable having the same physical dimensions but homogeneous insulation throughout. This comparison demonstrates the advantages of capacitance grading, where using materials with different permeabilities improves stress distribution, lowers peak electric stress, and enhances the insulation efficiency and operating reliability of high voltage power cables. Okay, there are some equations. Just we need to uh, replace the values, and finally we will have these equations, and we can just replacing the all of given values, we can find this one. So C1 over C2 is equal to 1.667. So this result highlights how both material properties and physical dimensions influence the overall capacitance distribution in multi-layer dielectric systems, which is particularly important in the design of cable and high voltage insulation structures. Okay, this slide continues the analysis by relating the capacitance ratio to the voltage distribution across the two dielectric layers. Since the charge Q is the same in both regions, the capacitance can be expressed as C1 is equal to Q over V1, and C2 is equal to Q over V2, leading to the relationship C1 over C2 is equal to V2 over V1. So from this, it allows that V2 is equal to 101.667 V1, considering the total applied voltage of 100 kilovolt. The sum V1 plus V2 is equal to 100 kilovolt, allows us to solve for the individual voltages, resulting in V1 is equal to this value and V2 is equal to this value. So this slide then proceed to evaluate the maximum electric field in the inner dielectric using the expression E max 1, these equations, where the given dimensions are R1 is equal to 1 centimeter, R2 is equal to 2 centimeter. Finally, the general expression for the maximum electric stress in a coaxial system is presented as G max is equal to this equation. So overall, this slide highlights the voltage is unevenly distributed across the electric layers depending on their capacitances, and how this directly affects the electric field stress within the insulation, which is critical for a reliable HV cable design. So here, this slide compares the electric field distribution in a cable under two different insulation conditions: non-uniform or graded insulation, and homogeneous insulation. For the given geometry, where the inner radius R2 is equal to 2 centimeter, and outer radius is 4 centimeter, and an applied voltage is 62.5 kilovolts. The maximum electric field occurs at the conductor surface and is calculated as 45.1 kilovolts per centimeter, while the minimum field at the outer boundary is 22.5 kilovolt per centimeter. So this shows a relatively more balanced field distribution. However, when homogeneous insulation is used with a higher voltage of 100 kilovolt, the electric field becomes highly non-uniform, reaching a much higher maximum value of 72.1 kilovolt per centimeter near the conductor, and dropping significantly to 18 kilovolt per centimeter at the outer surface. This comparison highlights that homogeneous insulation leads to a greater electric stress concentration at the inner conductor, which can increases the risk of insulation failure. So therefore, proper insulation design such as grading is essential to achieve a more uniform electric field and improve cable reliability. So this figure illustrate how the electric field varies with radius in a cable for the two cases: homogeneous insulation and graded insulation. In the case of homogeneous insulation, the electric field is highly non-uniform with a very high value near the inner conductor that rapidly decreases as the radius increases. This creates a strong electric stress concentration at the inner surface, which is the most critical point for insulation failure. In contrast, the graded insulation curve shows a more controlled and smoother variation of the electric field. By properly designing the insulation layers with different permeabilities, the electric stress is redistributed more evenly across the insulation thickness. As a result, the maximum electric field is reduced, and the difference between inner and outer stress level becomes smaller. So this demonstrates the key advantages of graded insulation. It minimizes peak stress and improves the overall reliability and lifespan of the cable systems. Okay, this is a very small things. Highlight the main practical limitation of using graded insulation in cable design. Although graded insulation is theoretically very effective in achieving a more uniform electric field distribution and reducing peak stress, its implementation is constrained by material availability. So this is a limitation of the grading system. Okay. This slide describes the intersheath grading, a method of cable grading. So unlike capacitance grading, this method uses a single type of insulating material throughout the cable, meaning the delivery is homogeneous. So how it works? This picture depicts a cable cross section connected to a transformer. So an intersheath is a metallic layer placed within the dielectric. This layer is then connected to a specific voltage through a tap transformer. So by applying control voltage to the intersheath, the total voltage across the cable insulation is divided into multiple stages. This step-down voltage distribution effectively lowers the electrical stress on the dielectric, especially in the inner layers where stress is typically highest. Okay, here in intersheath grading, while effective in principle, has several significant disadvantages that make it rarely used in practice. So these include cable joining is more complex and complication in fixing sheets potentials and damage during the installation, losses due to charging current. So these are some disadvantages of this method. Okay, this is an example present the analysis of 120 kilovolt 50 hertz single core underground cable with lead sheet focusing on its electrostatic performance. The cable has a core radius of 1 centimeter and internal sheets are at 2 centimeter and an outer sheets at 4.2 centimeter with a homogeneous insulation characterized by a relative permeability of 3.8 and a total length of 6.44 kilometer. The problem systematically guides us through key design calculations. First, determining the capacitance of each dielectric layer, followed by the total capacitance of the cable. It then examines the maximum electric stress at the conductor surface when the intersheath is ignored, highlighting the importance of electric field distribution. Furthermore, the example introduces the concept of stress control by asking for the optimal potential to be applied to the intersheath in order to limit the maximum electric stress to a specific safe value of 55 kilovolt RMS per centimeter. Finally, it evaluates the total reactive power equipment in kilovolt amp for both operating conditions, emphasizing the practical implementation of capacitance and electric stress management in high voltage underground cables. All right. So this slide focuses on the detailed calculation of the cable capacitance for the two dielectric regions and the overall equivalent capacitance. First, the capacitance of each layer is determined using the standard expression for coaxial cable. So we can use these equations. Using this relation, the inner dielectric capacitance C1 is the calculated based on the ratio of radial 2/1, so resulting in approximately 1.96 microfarad. This value shows that both insulation layers contribute significantly, but not equally, both due to their different geometrical proportions. So next, since the two dielectric layers are effectively in series, the total capacitance is obtained using the series combination formula. This yields a total capacitance of approximately 0.946 microfarad. The slide also verifies this result by directly applying the capacitance formula across the entire insulation thickness from the conductor to the outer sheets, giving a consistent value of about 0.947 microfarads. Overall, this slide demonstrates both the step-by-step layer-wise approach and the direct method, reinforcing the concept that multi-layer cable installation can be accurately analyzed either by decomposition or by using an equivalent single dielectric models. So part C focuses on evaluating and controlling the maximum electric stress in a cable with homogeneous insulation, while initially neglecting the effect of the internal sheets. In part C, the maximum electric stress is calculated using the standard logarithmic expression for cylindrical insulation, leading to a value of 83.6 kilovolt per centimeter. This result highlights that the stress is highest at the conductor surface and depends inversely on the radius and logarithmic ratio of the insulation geometries. In part D, the design requirement is introduced. The maximum electric stress must be reduced to a safer value of 55 kilovolt per centimeter. To achieve this, the voltage is recalculated using the same fundamental relationship between the electric stress, applied voltages, or voltage and cable dimensions. By arranging the formula, the required voltage corresponding to the reduced stress level is obtained. The final result shows that the voltage across the internal sheets becomes 38.1 kilovolt, demonstrating how introducing an internal sheets or modifying operating conditions can effectively limit the electric field and improve insulation performance and reliability. Part E analyzes the charging current and reactive power of the cable when an intershield is introduced, comparing the cases of open circuits and properly utilized intershield conditions. Initially, with the intershield open circuit, the charging current is calculated using the standard relation. I charging is equal to 2pfcv, resulting in a current of 35.7 amp. This leads to a reactive power of 4,280 kilovolt amp, indicating the capacitive nature of the cable under high voltage operations. So then we can find the I charging inner and total apparent power. Okay. This slide introduces the concept of cable effective in resistance, starting from the basic expression for the DC resistance of the cable conductor. So the resistance is given by RDC is equal to rho L divided by A. So where rho represents the resistivity of a conductor material, L is the length of the cable, and A is a cross-sectional area. This formula assumes a uniform solid conductor and provide the fundamental basic for resistance calculations. However, in practical power cables, especially standard conductors, this simple expression requires modification. So due to the helical arrangement of strands, the actual path followed by a current is slightly longer than the physical longer length of the cable. As a result, the effective length is increased by a small amount of delta L, leading to an approximate relationship. L prime is L plus delta L is equal to this one. So this means that the effective resistance of a standard cable is slightly higher than the ideal DC resistance. Okay. In item 3, explain the sheets effect denoted by lambda SAH as another contributor to the increase the effective resistance of the power cable under AC operation. This effect arises due to the presence of conducting metallic shields surrounding the cable core or cores. When alternating current follows through the conductor, it produces a time-varying magnetic field that links with the shields and induces a voltage in it. So, and in in item 4, introduces the harmonic effect denoted by lambda A as another factor contributing to the increase in effective resistance of power cables under AC conditions. So, and in this slide, explain how AC increases the effective resistance of a conductor compared to DC. So the effective resistance denoted as gamma effective is expressed as the DC resistance gamma DC multiplied by a factor that accounts for several additional effects, skin effects, lambda S, proximity effect, lambda P, shields effects, lambda SH, and additional losses, lambda A. Together, these components quantify how AC current distribution and electromagnetic interactions within them and around the conductor lead to higher resistance. So typically, the skin effect contributes between 2% and 24% depending on the conductor size, while the uh, proximity effect is negligible for single core cables, but can reach similar levels in three core cables. Shield losses are more complex and are analyzed separately, whereas additional losses are often around 20%. Okay, this slide introduces the concept of capacitance in a three-core belted cable and explained why capacitance is significantly more important in underground cables than in overhead transmission lines. In cable systems, the conductors are placed much closer to one another and also closer to the grounded metallic shields, which increases the electric field interaction between them. In addition, the insulation material surrounding the conductors has a dielectric permeability much higher than that of air, allowing the cable to store more electric charge for a given voltage. These two factors result in a much larger capacitance in cables compared to our lines. This increases capacitance affect the charging current, voltage regulation, and overall performance of the cable system, making capacitance analysis an essential part of the cable design and operation. So this slide explains the equivalent capacitance circuit of for a three-core belted cable due to the potential difference between the conductors and between conductors and the earthed shields. Two types of electrostatic fields and the resulting capacitances are established. Core capacitance between each pair of conductors, conductor earth capacitance between each conductor and the earthed sheets. So from this figure in this slide, um, the three core capacitance from the delta conductor, while the three conductor earth capacitance form a star connection with the shields as the start point. It is assumed that the capacitances are equal due to the symmetrical arrangement. So then this slide explains how to derive the equivalent capacitance and calculate the charging current for a three-core belted cable. So equivalent capacitance, this figure shows the final equivalent circuit for the cable's capacitance. So the circuit shown combines the star-connected core earth capacitance with equivalent star-connected capacitances from the previous delta star conversion. So this diagram 2 simplifies the circuit further by showing the total equivalent capacitance per phase as a single star connected capacitance. So finally, we can find the equivalent capacitance. Okay, this slide showing that how uh, uh, we can measure measurement of C and CC. So in the next slide, we will have some diagram. Let me go to this one. So total capacitance per phase of a three-core belted cable can be calculated based on these equations. So here, sorry, yes, we have C1 is measured capacitance. This test yields C1 is equal to 3 CE, and C is equal to C1 over 3. And C2 is equal to measured capacitance is equal to 2 CC plus CE. So, and finally, C3 measured capacitance can be calculated based on this. We will have this equation. C3 is equal to 1 over Cn, 2 Cn. Okay. We have, so this is an example. This example presents a solve problem for a single core cable. It calculates the following parameters for an 11 kilovolt 50 hertz cable. So maximum stress is to be 27 uh, 27 point yes, for 11 kV, we have this system for 11 kV, kilovolt, 50 hertz single core cable. It calculates the maximum and minimum electrostatic stress, capacitance per kilometer, and charging current. So we will have these capacitance equations finally. So C3 can be calculated based on this 0.3 times 5, and the V phase is equal to in three-phase systems is equal to voltage over square 3, and the natural capacitance Cn of this cable can be calculated based on this equation, and charging current also, as I told you before, we can use these equations. Okay, this is another example. So the capacitance of a three-phase belted cable are 12.6 microfarad between the three-core bunch together, and the lead sheets, and 7.4 microfarad between one core and the other one and two connected to shields. Find the charging current around by the cable when connected to 66 kilovolt 50 hertz supply. So we already find all of these capacitance, so we can just need to replace the values, and finally we can find the CC as a 1.6 microfarad, and core to natural capacitance can be find based on this equation, and finally charging current, we can just replace the values in these equations. So here, this is another example similar to the previous one. So we just need to find the charging current again. So first we can find Cn, and then replace in this value, in these equations, we can find charging current, and finally apparent power can be in three-phase systems can be calculated based on this equation, 3V phase IC. So this is a topic about current carrying capacity of underground cables. So the safe current Carrying capacity of underground cable is determined by the maximum permissible temperature rise. So the temperature rise is caused by power losses within the cable, which are dissipated as heat. So these losses include copper losses in the conductors, hypotheses and the eddy current losses in the dielectric shields and armoring, and capacitance grading is a technique used to achieve a more uniform electrostatic stress in a cable insulation in an ungraded cable. The the electrical stress is the highest near the conductor and decreases toward the shield. So this method replace the homogeneous dielectric with a composite dielectric consisting of multiple layers of different materials. The relative permeability epsilon r of each layer is inversely proportional to its distance from the center. So this strategic arrangement ensures that the electric field E is a constant across the dielectric as shown in the provided formula. I already discussed with you. E is equal to 2p epsilon 0 CQ. So we can find that one. Okay, this slide represents the thermal resistance as a key concept in heat transfer, particularly relevant to understanding heat dissipation in power cables. So thermal resistance is the measure of an object's ability to resist the flow of heat. It's defined as the ratio of the temperature difference between the two points to the rate of heat follow between them. So S is equal to heat following in a unit time temperature difference and P power dissipate as a heat measured in watts, and we will have this equation: thermal resistance is equal to T over P. So and also thermal resistance S is directly proportional to the length L of heat follow pass, as you can see here, the length, and the thermal resistance in inversely proportional to the cross-sectional area, uh, and uh, and this relation expressed by this one. So here chi is a constant of proportionality and is called a thermal resistivity. The unit of thermal resistivity is thermal ohm meter or degree centigrade meter per watt. Okay. This slide explains how to calculate the thermal resistance of the dielectric in a single core cable. So the thermal resistance of a dielectric S is calculated for the single core cable with conductor radius R and then internal shield radius R1. The thermal resistivity of the insulation is denoted by K. So to find the total thermal resistance and infinitesimal element of thickness dx at radius x is considered. So the thermal resistance of this element ds is equal to k times dx over dpx. So this formula is based on the general thermal resistance formula. S is equal to Ka all L, where the length of the heat pass is dx, and the area is the surface area of the cylindrical element, 2px per meter length. So the total thermal resistance S is then found by integrating the thermal resistance of this element from the inner radius R to the outer radius R1. So we already discussed about this one, so we just need to use these equations. Okay. Uh, this slide explains how to determine the most uh, permissible current loading. So when considering the heat dissipation in underground cable, the various thermal resistance providing a heat dissipation path area in series. So we have all of these parameters: permissible current per conductor, number of conductors, and or electrical resistance per meter length of the conductor, and S total thermal resistance, and T temperature difference between the conductor and the soil. So finally, we will have this one: permissible current I is equal to square 2T over N RS. This is very important. We will see in the example. This is the example here. So we have this example: single core cables to laid in the diagram in the ground. The core diameter between the begin 30 millimeter and the electric thickness 40 millimeter. The thermal resistivity of the dielectric is 5 thermal ohm meters, and the thermal resistance between the shields and the ground surface is 0.45 thermal ohm per meter. Length of the cable, neglecting dielectric and shield losses. Estimate the maximum permissible current loading if the temperature difference between the conductor and the ground surface is not to exceed 55 degrees centigrade. The electrical resistance of the cable is 110 micro ohm per meter length. So first, we can use this equation to find the thermal resistance of the dielectric of the cable, just replacing the values, and S1 can be simply find this value. So S2 also, thermal resistance of soil is 0.45 ohm. So S is equal to S1 plus S2 is equal to this value. So the current is equal to this value. We have one core conductor, and temperature is 55 degrees, and S is 1.45. So we can just replace the values and we can find the current. Okay. Uh, Cable faults. Cables are typically laid underground, either directly in the ground or in the duct, which reduces the chance of fault. However, if a fault occurs, it's difficult to locate and repair because the conductors are not visible. The most common types of fault in underground cables are open circuit faults, and short circuit faults, and earth faults. So we will discuss in the following slides for each of these faults separately. So open circuit fault, we have this fault. So when there is a break in the conductor of a cable, it is called open circuit fault. So by using of Mayer devices, we can find this resistance. The Mayer will indicate zero resistance in the circuit of the conductor that is not broken. It means that cable is okay. We have a short circuit, and when two conductors of the multi-core cables comes in electrical contact with each other due to the insulation failure, it is called a short circuit failure. And again, by using of Mayer, we can measure we can find we can check that whether we have a fault or not. So if the Mayer gives zero reading, it indicates short circuit fault between these conductors. So we have an earth fault, also known as a ground fault, occurs when a conductor of a cable comes into contact with earthed shields or the ground itself. To identify this type of fault, one terminal of a Meyer is connected to the conductor and the other terminal is connected to the earth. If the Meyer indicates a zero resistance reading, it confirms that the conductor is earthed and thus an earth fault has occurred. Okay, this slide introduces the fundamental concept of power factor in AC electrical systems. It is a critical topic for understanding the efficiency and performance of any electrical circuit, especially in industrial and commercial settings where large inductive loads are common. So power factor is a ratio that tells us how effectively we are using the electrical power delivered to a system. It is defined as the ratio of reactive power, kilowatt, to apparent power, kilovolt amp. A power factor of 1 or unity means all the power delivered is being used for useful work. A low power factor indicates that a significant portion of the power is not doing using useful work, but is instead cycling back and forth in the system. Uh, and What is the real power? Real power measured in kilowatt. This is a useful power that perform the actual work, such as running a motor, lighting a lamp, or heating a sensor, and so on. Reactive power measured in kilovolt amp, reactive or kVAR. This power is required by components like motors, transformers, and inductors to create the magnetic field necessary for their operation. It does not know useful work, but is essential for the function of these devices. We have apparent power measured in kilovolt amp. This is the total power that must be supplied to the circuit. It is the vector sum of real and reactive power represented by the formula. S2 is equal to P2 plus Q2. It is size of the power a generator or transformer must be able to produce to meet the load demands. All right, this slide focuses on the practical solution to the low power factor correction. The primary goal is to improve the efficiency of the electrical system by reducing the amount of reactive power that the utility must supply. So the main objective of power factor correction is to improve the power factor and reduce the reactive power burden on the entire power system. By improving the power factor, we can reduce the overall current in the system, which in turn leads to lower power losses and better voltage regulations. So how most industrial and commercial electrical loads like motors, transformers, and induction furnaces are inductive. So this means that they require and consume a large amount of lagging reactive power to create their magnetic field. So the most common and effective method for correcting low power factor is to add a capacitive load to the system. Capacitors, by their nature, generate leading reactive power. By strategically adding capacitor banks at the load or substation, we can generate just enough leading reactive power to counteract the lagging reactive power from the inductive loads. This effectively balances the system and reduces the need for the utility to supply as much reactive power. So to ensure effective correction, the size of the capacitor bank must be carefully calculated. So there are so many methods to calculate the size of the capacitor banks. Okay, this slide summarizes the significant advantage of correcting a low power factor. It highlights how this seemingly technical practice translates into tangible benefits for both the power system and the end user. So power factor correction reduces the total current drawn from the utility source by supplying reactive power locally with capacitors. The need for the source to provide this non-working power is minimized. So a lower current following through the transmission and distribution lines result in a significant reduction in power losses, RI2 losses. So this improves the overall efficiency of the grid and saves energy. So the voltage drop along the transmission line is directly related to the fall of both real and reactive power. By reducing the fall of reactive power from the source, power factor correction helps to stabilize and support the system voltage, ensuring that the voltage at the load remains within the acceptable limits. So this is crucial for the proper operation of sensitive electrical equipment. All right, this slide also introduced two advantages of an important method for managing reactive power in long transmission lines: shunt reactor compensation and series capacitor compensation. These techniques are critical for maintaining voltage stability and increasing the power transfer capability of the grid. Okay, this slide focuses on SVC, a key device in a modern power system. And SVC, static var compensator, is part of the flexible AC transmission system, as I told you, uh, which are designed to enhance the controllability and stability of power grids. Unlike the fixed capacitor bank that provide a constant amount of reactive power, and SVC can dynamically adjust its output in real time. So, and the SVC ability to provide dynamic compensation comes from its main components, which are controlled by high-speed electronics, the thyristor control reactor, or thyristor switch capacitor. So we can use these two type of thyristors. So the SVC uses a fast-acting control system to continuously monitor the bus voltage. If the bus drop indicating a need for more reactive power, the control system can switch on the TSC to inject reactive power into the grid. Conversely, if the voltage rises due to excess reactive power, the system can turn on to the TCR to observe reactive power. This rapid dynamic response provides a very effective means of providing voltage support and improving the overall stability of the power grid, especially under transient or varying load conditions. Okay, this slide focus on the crucial practical practices of testing and maintaining capacitor bank. So these banks are a vital component of power factor correction systems. So the main purpose of testing a capacitor bank is to verify its functionality and performance. Over time, capacitors can degrade due to factors like heat, voltage stress, and age. Routine testing helps to identify any underperforming or faulty units before they lead to a system failure, thereby ensuring the reliability and the efficiency of the power grid. So several key procedures are performed during the routine test, including the visual inspection, capacitance measurement, current measurement, and fuse break check and discharge time test. Okay, this slide focuses on two common types of voltage fluctuation that, uh, sorry, uh, first outline the learning objective of this module, this regarding the uh, power quality. So, including the understand the definition of the actually definition and significance of voltage sags and soil, total harmonic distortion, and understanding the techniques used and power system stability. Okay. What is the power quality? The power quality refers to the degree to which the voltage, frequency, and waveforms of power system conform to an ideal sinusoidal waveform. So, why is it a concern? So, modern electrical systems like power electronic devices make some, they have some switching, so they are working in different frequency. So they will make disturbances in the sinusoidal waveforms. Um, what is the this slide focus on two common types of voltage fluctuations. Sorry, that are key indicators of power quality issues: voltage sags and voltage soils. These events can have significant effects on electrical equipment and the overall stability of the power system. So voltage sags is a temporary reduction in the root mean square voltage. The voltage typically drops to a value between zero point 0.1 and 0.9 per unit, 10% to 90% of nominal voltage, and lasts for a short duration, usually from a half cycle to a few seconds. Voltage soil is a temporary increases in the RMS values, voltages. The voltage rises to a value typically between 1.1 and 1.8 per unit, or 110% to 180% of the nominal voltage for a short duration. And voltage soils are often caused by the sudden disconnection of a large load from the system. This can cause the voltage to momentarily spike before the system's control mechanisms can stabilize it. They can also be caused by certain types of faults, such as ground fault on and um, and uh, one phase of three-phase system. And Voltage sources are particularly damaging. They can lead to overvoltage related equipment failures, cause insulation breakdown, a lot of things in motors and transformers and so on. Okay. This slide delves into the concept of THD, significant measures of power quality. It explains what harmonics are, why they are a problem, and how we quantify their presence in a power system. In an ideal AC power system, the voltage and current waveforms are perfect sine waves with a single fundamental frequency. It means, for example, 50 Hz and or 60 Hz. However, in reality, this waveform can become distorted. Harmonics are sinusoidal waveforms with frequencies that are integer multiples of the fundamental frequency. For example, the third harmonics is at 150 hertz, and the fifth is at 250 hertz, and so on. They are primarily created by non-linear loads which do not draw current in a smooth linear fashion. So and so on. All right. This slide highlights the importance of industry standards in regulating and maintaining power quality. This standard provides a framework for defining acceptable limits for power quality issues, helping to ensure compatibility between different electrical equipment and stable, reliable power grid. We will focus on two of the most significant standards, IEEE 519 and IEEE 6061 000 family. So IEEE 519 recommended practice and requirements for harmonic control in electric power systems. This standard published by the IEEE is a critical document for managing harmonic distortion. IEC 61 000 is a comprehensive series of international standards from the International Electrotechnical Commission. It addresses the entire field of electromagnetic compatibility, showing that electrical and electronic equipment can operate correctly in its electromagnetic environment without introducing unwanted disturbances to other equipment. All right. This slide presents the practical solution for mitigating the harmful effect of harmonics. So, passive, we can now use different uh, different methods, passive filters, active filters, or isolating transformers. So, passive filters are the most common and traditional solution for harmonic mitigation. They consist of a simple combination of inductors and capacitors. Active filters are a more modern and dynamic solutions that uses power electronics, and isolation transformers is uh, special types of transformer with unique winding configurations. So the choice of solution depends on the specific power quality issue, the budget, the sensitivity of the equipment should be protected, and so on. All right. This slide introduces a critical and complex topic in the power system stability. It is the ability of the electrical grid to maintain a state of equilibrium and continue operating after disturbance. Stability is essential for preventing cascading failures and widespread blackouts. Power system stability is the ability of the system to remain in a state of operational equilibrium after being subjected to a disturbance. A disturbance can be anything from the minor fluctuation in load to a major event like a short circuit or the losses of large generators. And we have different types of stability: steady state stability, transient stability. Steady state stability refers to the ability of the system to maintain equilibrium under small gradual changes in load or generations. Transient stability is a more challenging and critical form of stability. It is the ability of the system to remain in a state of equilibrium after a large sudden disturbance, such as major fault, a sudden change in load, or the losses of large generators. Okay, this slide outline the learning objective for this module, the grounding. Uh, Grounding practice. So uh, the fundamental concept of grounding or earthing in an electrical system. Grounding is not just a technical requirement; it is a single most important safety practice in electrical engineering. It is a critical line of defense for both equipment and personnel. So, what is grounding? Grounding is is the practice of connecting an electrical circuit or equipment to the earth. The earth, with its vast size and conductivity, is used as a zero potential reference point. This connection creates low resistance path that allows fault current to follow safely into the ground. This is deliberate and well designed path, distinct from the normal current carrying conductors. So the primary purpose of grounding are multi-faceted and crucial for the reliable and safe operation of any electrical systems. So this slide explored the practical application of grounding in different parts of power system. The design and the arrangement of grounding system vary depending on the specific location and the level of safety and protection required. We will look at three key areas: transmission lines, substation, and consumer facilities. And in HV transmission line systems, grounding is crucial for protecting the lines from lightning strikes, uh, and ground wires or shield wires. These are conductors typically uninsulated that are run above the phase conductors at the top of the transmission towers. The ground wires act as a shield, intercepting lighting strikes and safely diverting the high current lighting surge to the ground through the steel tower structure. This prevents a direct strike on the phase conductors, which could cause an outage or damage equipment. Regarding the uh, consumer facilities, the grounding system in a building is designed to protect people and equipment from electric shock. So we have a grounding electrode system. This is a main connection to the earth, typically consisting of one or more ground rods, metal plates, or a ground ring bored around the foundation. This slide emphasizes the critical role of industry standards in the field of electrical grounding. These standards are not just recommendations, they are a set of rules and guidelines that must be followed. So, importance of standards: grounding practices must be highly regulated and consistent across different installations. So standards provide this necessary framework, ensuring that a grounding system design and installed in one location will provide the same level of safety and protection as a system elsewhere. They provide clear rules for designing, installing, and inspecting grounding systems, which is essential for both manufacturers and engineers. So we have IEEE 8 and this is standard from the IEEE focus on the design of a grounding system for AC substations. We have IEC 364. This is a comprehensive international standard from IT. It addresses the safety of electrical installations within buildings and is widely adopted globally. And we have a load and national codes. In addition to international standards, every country has its own specific electrical codes. A prime example is National Electrical Code, or NEC, in the US. So these codes often incorporate elements of international standards, but are tailored to local practices and regulations. They provide detailed legally enforceable rules for grounding in residential, commercial, and industrial facilities, ensuring a high level of safety for everyone. Adherence to these standards is non-negotiable for everyone working with electrical systems. So slide addresses the critical aspects of grounding safety, the dangers associated with grounding resistance. A grounding system is only effective if it provides a very low resistance path for fault currents. If this resistance is too high, the system safety function is compromised, leading to severe hazards for both people and equipment. So a high grounding resistance means that the electrical connection between the system and the earth is not as conductive as it should be. The path for fault current to follow the safety into the ground is impeded. This can be caused by various factors, including poor soil conditions, improper installation, corrosion over time. So corrosion also is a most important things. So what will be happen? Effects of unsafely, we will have electric shock hazard and touch and step potential effect. So regarding the electric shock hazard in a fault condition, for example, a live wire touching the metal frame of a motor, the fault current will follow through the grounding system. If the grounding resistance is high, the voltage of the equipment frame will rise to a dangerous level rather than being safely dissipated into the ground. So this creates a severe electric shock hazard for everyone who touches the equipment. The circuit breaker may also not trip as the current is not high enough to activate it. So touch and step potentials during a fault, a high grounding resistance can lead to a significant voltage drop across the surface of the ground near the fault location. This creates two specific dangerous touch potential and step potential. Okay, this slide focus on the crucial practice of grounding resistance measurement. Uh, Grounding system is only effective if its resistance is low enough to safety dissipate fault occurrence. So this measurement is a fundamental part of an electrical safety and maintenance program. So the primary purpose of measuring grounding resistance is to verify that the grounding system is performing as designed and that its resistance is within the safe limits specified by standards like IEEE 80. Regular periodic measurements are essential because soil conditions can change and corrosion can increase resistance over time, compromising the system effectiveness and safety. So the most common and reliable method for measuring grounding resistance is a fall of potential method. This technique uses a specific arrangement of probes to get an accurate reading. It is also known as a three-point test because it requires three separate points of contact with earth, the main grounding electrode, current probe, and voltage probe. And The procedure is a placement, a current probe, and a voltage probe are placed in the ground at a specific distance from the grounding electrode under test. So the probes are typically placed in a straight line with the voltage probe at a distance of about 62% of the total distance between the current probe and the electrode. Okay, I want to thank you for all of your attention. Sorry, it takes 1 hour more because there were um, a lot of actually um, slides and so on. So inshallah, it was useful for everybody.